hay nadie. ¿Por qué les gustará llegar a la mera hora?
Porque estás en tu casa, tal vez.
Oye, luego tengo una estudiante y me dice dos cosas bien interesantes. La primera es que no funciona si no está
Ya,
bajo
la
presión.
doctora está ahí. Pásala
Ok,
a panelista.
ok, déjame ver, promote panelist, aquí.
Okay.
Ok.
Hi, good morning. Valeria.
Hola,
Hola, Valeria.
hola, ¿qué
Hola,
tal?
buenos días.
¿Cómo les va?
Muy bien.
Bien, gracias.
Do you prefer to speak in English or Spanish?
La presentación es en inglés, pero así hablo en castellano.
Ah, ok. Mucho gusto, Valeria.
Un gusto, gracias por la
Gracias por
invitación.
aceptar
Julio.
la invitación.
Sí.
Gracias.
Y no, un gustazo conocerla.
Es recurrente esta conferencia, ¿no? La hacen seguido.
Sí, cada año ya tiene, solamente creo que 2 o 3 años no se ha podido llevar a cabo. Y ha estado estuvo particularmente en una ciudad, San Luis Potosí, aquí en México.
Sí.
Luego se movió a otra ciudad, a Puebla, y ahora nos lo trajimos aquí a Guanajuato.
Guanajuato. Ahora es online, así que.
Y de hecho, el año pasado estaba organizada para hacerlo presencial.
Sí,
Y pues desafortunadamente con la pandemia, pues ahora lo
claro.
convertimos a virtual. Para algunos speakers eso fue bueno porque, bueno, pues ya no se
Sí.
tuvo que viajar.
Para mí es bueno porque estoy dando clase, de hecho en 2 horas tengo que ir a dar clase.
Sí.
Sí, es más fácil. Sí, sí.
Entonces eso nos ha de alguna manera ayudado. Sobre todo para algunos speakers que están en Europa, y entonces les es más complicado viajar.
Sí, sí, sí.
Y ahora, como dice, pues ya prácticamente da la plática, está un par de sesiones.
Sí, es más, por un lado es más fácil participar, por el otro es más, uno se conoce menos con la gente, ¿no? Que es la idea de ir a un lugar que se conoce.
Ese ha sido el problema. Hemos tratado de poner alguna estrategia, sobre todo porque terminan las sesiones y la gente quiere seguir platicando, ¿no? Y entonces
Sí,
en la comida o en
sí,
los breaks, la gente discute los temas más, que esa es
sí,
un poco la idea, ¿no? Que discutas con los expertos
sí.
en ciertos temas, pero pues es complicado.
Hay una forma, tal vez medio tarde, pero estamos a la mitad de la conferencia. Bueno, quedan 2 días. Estas aplicaciones se llaman, por ejemplo, Special Chat o Gather Town, en la que uno puede loguearse y simplemente encontrarse ahí. Y es fácil hacer cuentas para usarlo sin ningún sobreprecio, así directamente.
Sí, sí.
Hasta 50 personas por no sé cuánto tiempo uno puede hacer, depende cuánto es, pero Gather Town, sí. O Special Chat, se puede hacer un sitio de la conferencia y que la gente se encuentre. Esa es una.
Hay,
Yo lo
hay
uso.
un gather down, doctora
Sí,
Molina,
sí, del
de la
simposio.
conferencia.
Ah, tienen,
Ajá,
está bien. Y
sí.
porque yo encontré a veces. Gather Town a mí no me gusta, porque parece un videojuego, pero
Sí,
pero
es
las otras
verdad.
sí.
Pero como usted dice, es gratis y
Sí,
fácilmente lo
sí se
pueden hacer
puede.
rápido. Y
Sí.
es
Es una
lo que
alternativa,
tiene.
una posibilidad. Una posibilidad.
Okay. Well, time I guess it's 9 o'clock. So I guess I start the session. So good morning, everybody. We are going to start the third day of it's very long, the name of the Congress, International of Science. Actually, for me, it's too long. Let me try to read. The International Conference on Science and Technology of Complex Fluids. We promised to change the name maybe for the next next year because it's too long. But it's a pleasure for me to present to the Professor Valeria Molinero. She is a distinguished professor and Jack Apec Simon Endowed Professor of Theoretical Chemistry at University of Utah. She has a lot of papers. Her research is very, very interesting. And I want to thank Julie for her to accept the invitation. And thanks, Valeria. You can start your talk. I guess you can share.
Yeah, thank you. Thank you, Julio, for the invitation. I am absolutely delighted to be here, and I'm very grateful for having this opportunity to present work we have been doing very lately. This is work that doesn't have a lot of complex fluids, hopefully a little bit, but is on understanding the mechanisms of formation of porosilicate crystals. And this is work that was done at the University of Utah, mostly by Devdas Taval and Reza Bertolaso, that are two postdocs in my group, and builds on work originally by Abhinav Kumar, that was a grad student and started with a related topic. And our collaborators, Subho Banik and Subramanian Sankaranarayan at the University of Illinois at Chicago. And when I talk about porosilicate crystals, I actually am referring to zeolites. And zeolites are crystalline materials with order 1 nanometer pores. And these pores can be in 3 dimensions and interconnected. And there's a large variety of zeolites. This is because silicates have a structure in which you have a central silicon atom with 4 oxygens. And these can really have a flexibility of silicon-oxygen-silicon angles that allow you to make many types of networks. And this diversity is actually common to the silicates. So there is a huge variety of silicates that exist in nature and synthetic. But when we look at the silicates that are in the phase diagram, the ones that are stable, the zeolites are not there. The zeolites exist only as metastable crystals. In the phase diagram of the silicates, if we look at the low pressure range, that is where the zeolites are made, what you have is that the region of stability at room temperature is quartz. And also, if you go high enough, you end up forming, for example, cristobalite, that is the first one that melts to the liquid at almost 2000 Kelvin. But the zeolites are synthesized under the conditions here shown in red. These are conditions in which we are deep into the region of stability of quartz. And then the zeolites can be made to stay without melting up to temperatures of about 1000 Kelvin. So these are metastable crystals, and because of this, it may look like they're very difficult to produce or do not exist. But this is not at all the case. Actually, zeolites are the most used solid catalyst in the chemical industry, and they're a multi-billion industry. At this point, the zeolites are used in multiple applications, and maybe the one that is the most common and less fancy is for detergent builders and absorbents, because they have these pores and they're used to absorb other molecules. However, most probably the application that calls for more development of new zeolites and more tailoring of the pores are the ones related to chemical catalysis. That is a small fraction, but we're talking about 34 billion, so it's a pretty large still. And in this case, the application that requires more and uses more zeolites is a petroleum refinery. So catalytic cracking, reforming, refining of petroleum, all of these use zeolites transform from the heavy oils into gasoline, and also to convert between different compounds. So there has been a huge work on developing new materials, and particularly in the interest on synthesizing zeolites that have distinct size and connectivity of the pores that can be used to tailor chemical reactions. And the number of zeolites that exist in the market is very impressive. There are 260 zeolite polymorphs to date. So there are 260 ways of putting these silicates into orders that have distinct size of pores and connectivity. Some of the crystals are shown here. You have small pores, large pores, but when I say small and large, they're always within the nanometer. But this is just a small amount compared to the number that have been predicted using molecular modeling. You can have, depending on the estimates, from about 300,000 possible zeolites to about 2 million zeolites. So the question is, why don't we access other zeolites during the synthesis conditions? And Analysis of the stability of these alternative zeolites that do not yet exist indicate that the issue is not the energetics of the zeolites themselves, but how do you access these polymorphs through the crystallization pathways. So that means that it's paramount to understand what is the mechanism by which these zeolites form. And the topic of synthesizing new zeolites is actually not new, and it has been a boom on this area since the 60s. So I don't know if you can call a boom for something that has going on for 60 years or more. But the main way that people have of controlling the crystal that you are going to get, the polymorph, the order of the channels, is by using different templates that these are structure-dating agents. And these structure-dating agents are molecules that typically are cations with these chains. So these tetralkylammonium cations, they can be inserted inside the channels, and with this, they template the shape of the channels. This is the understanding to date, but the question is, how do the zeolites form? How do they get into the channels, these structure-dating agents, and at which stage they are directing the formation of these channels, at the nucleation stage, at the growth stage, and how do they decide that they're going to form one type of zeolite or the other? At this point, the crystallization mechanism of the zeolite is not understood. And this is in part because it's an extremely challenging system to work with. The synthesis of zeolites is performed typically under what is called hydrothermal synthesis conditions, that is at high pressure and high temperature. So you have a solution in which you have a structure-dating agent, that these are tetralkylammonium cations, and a silica source that, let's say that is a monomer in this case. And the temperatures needed for hydrothermal synthesis are close to 200 centigrades. And because the boiling point of water is below, you have to do this in a vessel that can reach high pressure, like an instant pot, but for zeolites. And in this vessel, the first step of the synthesis is known to be the polymerization of silica that goes from monomers to oligomers and then nanoparticles that segregate. And these nanoparticles have already silica that is polymerized, a structure-dating agent that are cations, and also water. And within these nanoparticles, people have detected these to be amorphous and between 3 and 9 nanometers in size. You can see the crystallization of the nanoparticles, and these crystal nanoparticles then aggregate and grow into larger crystals. All of this is happening at high pressures and at the very harsh conditions of pH about 11. Despite the difficulties on following this synthesis, there have been many studies, particularly recently, in which there is imaging, but this imaging is ex situ because the conditions of synthesis do not allow it to really map what is going on under the high temperature, high pressure, and high pH of the synthesis. I'm showing here results from a recent study in which, in the experiment, they do imaging of the synthesis of silica light. And what I'm showing in the first picture of their work is the diameter of the nanoparticles as a function of time and temperature. The protocol is that first they heat at 90 centigrades, then they heat, nothing happens truly, they polymerize, and you see that the nanoparticles, they reach a size of about 5 nanometers. And then even when it's heated to 130 centigrades, that is almost 400 Kelvin, then you start to see a change, not in size, but it's a change in crystallinity. And this change in crystallinity is shown below. There is what is identified as an amorphous nanoparticle in the beginning. And then you see some fringes within the nanoparticles. We're talking about a few nanometers that denote the appearance of crystallinity in the system. Now, for this transformation is within the particles. And finally, the particles aggregate in the process of oriented attachment to produce larger aggregates. And this is where you see the change in size. What is most intriguing is that experiments, not only this one, but multiple experiments, when they sample the state in the beginning in the amorphous nanoparticle, what they see is that the structure of the amorphous nanoparticles evolve prior to crystallization, before you can detect actual crystals, attaining a local and medium range order and a solubility that is similar to the one of the zeolites. And the main question has been, what is the nature and origin of this intermediate order? What is that is going on before the zeolites form? Now, there are many possibilities, and I'm going to explore one in this case, and then tell you what I think is really going on in the synthesis of the zeolites. One possibility is that there are other phases participating in the mechanism. And one hint of why other phases could be part of the mechanism is that there are other metastable phases in the same landscape of the synthesis where the zeolites form. This is more evident when we look at the nature of the structure-directing agents used that are surfactants for the synthesis of zeolites. If we have a molecule that looks like this, it's a tetralkylammonium cation, and it has 3 methyl groups and a chain that has up to 6 carbons long, it makes a zeolite, what is called MFI or silicalite, the most common zeolite. Then between 6 and 10, it makes a mixture of zeolites that are the crystals I described before, and mesoporous silicas, and these go through mesophases. And if they're longer, they only form mesoporous silicas. Now, mesoporous silicas form in the way that involve mesophases that template the formation of large pores, and around the large pores, different from the zeolites, the silica is not crystalline but is amorphous. There are many examples that probably you're familiar with, like MCM and many other type of absorbents. Now, this poses the question of whether the mesophases can be involved in the synthesis of zeolites and facilitate the nucleation by decreasing the nucleation barriers. This is a sketch in the following. Let's assume that we're looking at the free energy of formation of a zeolite as a function of the reaction coordinate from the isotropic amorphous phase. You can conceive that there is a large barrier to go from the liquid to the crystal because there is a big difference in the structure of these two phases, resulting in a large interfacial tension that really controls the magnitude of the barrier. However, if you had another phase that has intermediate order between the parent phase and the crystal, then you could essentially split the barrier in two if you go first from the liquid to the mesophase and from the mesophase to the crystal. So this would allow for smaller barriers, and these barriers would accelerate the reaction and also direct towards the final polymorph. That means that it is conceivable that a mesophase or any intermediate phase could facilitate the formation of zeolites by providing a loose ordering of the silicates and the organic cations that is commensurate with the species in the crystal. So they're sort of doing half of the work, and then you only have to crystallize the silicates. So these are things that we explore. So what I'm going to show you today is a simple model for zeolite crystallization with tunable mesogenic character, then address the question of whether mesophases can be involved in the nucleation of the zeolites, and then when does the zeolitic order emerge under synthesis conditions, and what is the smallest size of zeolite that could be synthesized, because there is a big push towards making smaller and smaller zeolite nanoparticles. There are many challenges on using molecular simulations to address the question of zeolite synthesis, and that's why it was not done before. This is because the synthesis of zeolites convolute two types of rare events. One of them is the phase transition, that you have a barrier to go from the initial amorphous phase to the zeolite. And this barrier is mostly controlled by the surface tension of the zeolite interface and the difference in chemical potential between the initial and final phase. So this is one type of rare event. But the other that happens at each point that we're going up the barrier, you have to transform the silicate network, and to reconstruct the silicate network, you cannot just break and reform the bonds as it would happen, for example, in the silica melt at 2000 Kelvin. To reform the silicate network, you need to do at room temperature, at normal, like 200 centigrades, you need to have a chemical reaction in which you are opening and closing the silicon-oxygen-silicon bond. And this involves the reaction of hydrolysis and condensation. So each step that you are reforming the network, there is this series of reactions coming back and forth, and they're catalyzed by a very high pH. So in our case, we don't care too much about the chemical reaction because the chemical reaction is perpendicular to the reaction coordinate. And by this, I mean that accelerating the chemical reaction makes all the reactions, all the synthesis go faster, but does not impact the actual magnitude of the barrier for nucleation. So because of that, our goal in this modeling is to produce a model that represents properly the stability of the amorphous and the zeolites and any other intermediate phase, but does not take into account the chemical reactions. So for that, what we do is we don't use oxygen, we just have a coarse-grained particles, and we have like 2 silicon atoms that each of them is a CO2, and these silicon atoms can open and close the bond without the need of a catalyzed chemical reaction. So we model silica as a single particle that we call T because it's tetrahedral, and this tetrahedral particle has preference for angles TTT that are the typicals in zeolites. That is quite complicated angle distribution. Then we need to have also a model for a structure-editing agent. And because we want to test the hypothesis that mesophases could be involved in the formation of zeolites, we use as a structure-editing agent a single particle. It's very simple to model these tetraalkyl ammonium cations, but this particle has a frustrated attraction with T that promote the formation of mesophases, and I will show in the next slide. And the third component of our model is water that hydrates the system, and we treat water as either implicit or a monatomic water model. So these models are extremely efficient because they are based on short-range interactions and also the coarse grain, and they don't consider the chemical reactions. I told you that we are going to build models with mesophases. So let me, in sort of a detour, tell you a little bit about the model that we did in 2017, in which we show that you can produce the same mesophases as block copolymers by using 2 particles that are not connected. So maybe some of you are familiar with the physics of mesophases, and this physics appears because there are typically two pieces in a molecule or in a system that want to segregate, they want to separate, but they are connected, and that frustrates the phase separation. So the microphase separation is because there is a will for the red to avoid the blue and just go with the red, and likewise for the blue to avoid the red. But these 2 particles cannot get apart. Now, how do we model the same, or we mimic the same type of behavior if we have 2 particles that are actually not bound? We develop a model in which we consider 2 types of free spherical particles. They don't need to be spherical, but this is the simplest case, and the simplest case in which A and B have the same sizes. Then we can consider that to encode the frustrated attraction that leads to the formation of mesophases, we have a strong AB interaction that mimics the presence of the chemical bond. But of course, eventually these 2 particles, they are attracted more. The energy versus distance is shown here. So AB are attracted strongly, but they can move apart. The repulsion is encoded in the size of the particles. So in the case of these 2 particles, the repulsion is encoded in the fact that AA and BB want to be so that the AA and BB distances of attraction are shorter. So A and B want to be together because they have a stronger energy of interaction, but they cannot get very close. And this wanted to be together but cannot get very close is what produces the same type of repulsion that you can see in the block copolymers. And we found that the ratio of the minimum of the same type of interaction versus the cross interaction can be very small, like 4% larger, to suffice to stabilize mesophases. And the mesophases that they are formed depend, in this case, on the proportion of the A and B particles, the red and blue particles, and you can form with 50% of each lamella, or 2/3 you form gyroid, and 75% you form hexagonal. These are the same as in block copolymers, but now you can add new particles and go from one to the other. And the phase diagram we have for this system is equivalent to the one of the block copolymers. But again, the difference is that in the block copolymers, every time you want to change the fraction of red and blue, you have to synthesize a new molecule that has different proportions. While in the model that I'm presenting here, you can just add more of the red particles or more of the blue particles and you move, so you have a 2-component mixture. So what I showed before is the formation of mesophases. If we now add that one of the two components has the size of silica, the other has the structure, the 18 agent sizes, and we further add tetrahedral preferences for the order, angular preferences for the order of silica bonds, what we can do is generate spontaneously many zeolites, clathrates, and mesophases. And I'm showing here the crystal phases. So you can form clathrates, zeolites. This zeolite SGT is a clathrate also, but has different pores. Hexagonal zeolites, AFI zeolites, that is one that is known also, is a very well-known material. Gyroidal zeolites, 3 different types of gyroidal zeolites. And also you can form lamellar zeolites. So what you can see among these is that the hexagonal, gyroidal, and lamellar that are shown in blue, all of them build on pores that are typical of mesophases. So you can have zeolitic order built on top of lamellar, gyroidal, or hexagonal order. And this poses the question of whether this order intrinsic below in the mesophase is facilitating the nucleation. And I'm going to discuss mostly today one of these two zeolites, this one that is in the middle of the gyroidal one, that is called C1. And for this one, what we did is we take the zeolite, and we know that we can take the zeolite, and depending on the conditions, you can have a metastable gyrode phase, and you can melt to the gyrode and then to the amorphous. But this original model we have that has a gyrode phase as a stable one, we can then tune the interactions between the silica particles to make it disappear and become more and more metastable until it becomes unstable. So what we did is develop a series of models that have ongoing from A with a metastable mesophase to B that has, stable mesophase and metastable. B has only a metastable mesophase, and then C and D do not have any mesophase, and we want to see whether the mesophase can be involved in the nucleation pathway. We analyzed this for all the models, but in a nutshell, what we found is that it is possible for a mesophase to be part of the nucleation pathway of the zeolite, even when the mesophase is unstable. So even when it's metastable or unstable, you could have that within the amorphous phase, there is a small fluctuation, a small like nanoscopic fluctuation that produces the mesophase. And because this mesophase decreases the cost of the surface of the zeolite, this one precedes the formation of the zeolite, and the zeolite grows inside. And this can lead to non-classical mechanisms in which the critical nucleus, the one that goes over the barrier first, is the one of the amorphous to mesophase transition, as you see in the free energy barrier as a function of the size, the number of silicates in the particles. So you could have that first you form a gyrode, and the gyrode eventually grows into a zeolite in a way that seems seamless because the barrier for the gyrode to zeolite is very small. However, we also find that as we change the models and we make the zeolite less and less stable, what happens is that we need less and less of the facilitation of this mesophase because it's more difficult to produce the fluctuation. So if we go into conditions in which the stability of the mesophase goes down, I mean, the free energy goes up and up, the cost of producing the mesophase fluctuation is very high, and eventually the nucleation just happens through what is called a classical mechanism. We go directly from amorphous to zeolite, and also the barriers can be smaller. So that means that there is a possibility in these complex crystals to be mediated by a mesophase, but this is only if the mesophase has an accessible range of interactions or stabilities. Moreover, if we look at the phase diagram of these mesophases, it's a complicated phase diagram. When we look at where would be the conditions of zeolite synthesis, what we find is that the conditions of synthesis of zeolites happen at temperatures that are high for humanity, like 200 centigrades, but they're very low compared to the melting point of the zeolite. The melting point of zeolites is above 1000 Kelvin. That means that we are at most than 50% supercooling, and under these conditions, what we conclude is that the barriers for the direct formation of the zeolite are extremely low, so you don't need facilitation, while the zeolites can help to produce the more unstable zeolites because they have a lower melting point. In most cases, what we conclude is that the stability of zeolites is so high that does not require the help of another phase. Moreover, we find that the barriers are very small for nucleation, and the critical nucleus size, the one that is at top of the barrier for the formation of the zeolites, really is very small. It's in the order of a few silicate units. And this is very small compared to the unit cell of zeolites that are typically in the order of 100 silicates. So what we know is that a small fraction of the cell is enough to go downhill into the formation of the zeolite. That poses the question of at which stage does the crystal order emerge during the synthesis? Because I told you before that we have the amorphous initial solution with the monomers. These monomers polymerize through this chemical reaction that we are modeling in a simplified way. And when they're polymerizing, they may already form the crystals. So the question is, are they coupled, the polymerization and the formation of the crystal? Or they get to the amorphous phase, and within the amorphous phase, we see the emergence of the crystals that then aggregate and they form nanoparticles and aggregate. Our model, despite its simplicity, it has the advantage that is the first that I will show you. It reproduces both the polymerization and the crystallization for silica. That's why we can address this question about whether they are intertwined or not. Here I show, for your comfort, if you look at this, that the distribution of a species with n silica networks, this is the speciation of the silicate species in the experiments and the simulations, is the same as a function of the advance of condensation. So our model is able to reproduce the polymerization of silica, and now I'm going to show you the results of across the polymerization and formation of the crystals at high temperatures. And these are temperatures above the ones of hydrothermal synthesis. We start with the silica, here shown in green, and a structured iodine agent that are shown as orange balls. And the amount of water in this case is low relatively, but these are conditions that exist on silica, on synthesis of zeolites. You start seeing the polymerization, they form aggregates, these aggregates can come together, and these balls already have inside a distribution of channels that are porous. These are porous silicates already with channels that have a distance that is the same as in the zeolites. This is more clear in the graph below that shows the amorphous and the zeolite, and you can see in this case in green the silica, and in red the structured iodine agent that fills the channels. So the channels are pretty similar in the amorphous and the zeolite, although the structure of the silicate themselves look completely different. One is ordered and crystalline, and the other, it looks like it's not porous, but it's porous, it's just disordered. So there are accessible pores already in the amorphous phase, and you can stop the synthesis at the amorphous level and really have already porous materials, and this has been shown to have catalytic properties. So the accessible pores are the same in the crystal and amorphous. So at high temperatures, the polymerization on one step and the crystallization are well separated. You can distinguish these two steps. When we go to lower temperatures that are lower, but they are lower temperatures compared to the melting point, but they're still pretty high. These are the conditions of synthesis of zeolites. Then what you see is that in the polymerization, already you start to form pieces that have much more order. And these pieces come together and form something that is a glassy state. We are at temperatures that, despite being relatively high, are already intersecting the glass transition temperature for silicate that are hydrated. For reference, the normal silica without water, without SDA, has a glass transition that is at about 1200 centigrades. So the glass transition is very high. When you add water, you start coming down. And this is where there's an intersection at about the conditions of synthesis of zeolites. That's why the particles are not spherical, and these particles that are not spherical are consistent with the shape of the particles that are found in the synthesis conditions at comparable temperatures. Now, these particles that we call amorphous are already having some order that is zeolitic. You can see that in the large rings, and if we do a further analysis, there are pieces that look like zeolites, but these pieces are very small. And moreover, what we can tell is that the pieces that build the zeolite in the polymerization can have different order, and the order that you get depends on the water content. They can form more compact aggregates when you have more time to let them come together. And the order before the crystallization in the polymerization does not match any of the topological pieces that are present in the zeolites. So we conclude that the precursors along the polymerization pathway are not the building blocks of the crystal that is going to emerge after the synthesis. The crystal nucleation does not occur directly from solution. It happens mostly by developing order within these aggregates that are glassy. We have also shown that that the distribution of a speciation of different particles with different number of neighbors in silicates are, first of all, in agreement with the experiments. The experiment is the blue, and the simulations at 2 temperatures are the red and the green. And based on this analysis, we can also conclude that there may be some degree of crystallinity in these systems. But most importantly, our results, in which we see the crystallization already happening inside the amorphous phase, are consistent with the fact that the structure and solubility of the nanoparticles evolve, both of them, between amorphous silicon zeolites before the crystals are detected. So what we think is the mechanism of formation of the zeolites is that this intermediate order that originally we thought it could be a mesophase is actually the formation of a small crystallites within the nanoparticles. So let's say we have a nanoparticles that is 5 to 10 nanometers in diameter. And these nanoparticles are relatively small, and even compared to the unit cell of the zeolite, they're not very large. But the critical nucleus that makes the zeolites at the conditions of synthesis contains like 4 or 5 units. So we have like thousands of silicate units, and 4 or 5 of them suffice to make a critical nucleus. As the barriers are extremely low, what you have is that these barriers allow you to form multiple crystallites everywhere in the sample. And all of these are going to compete to grow, but they are competing to grow under conditions for which the mobility of the silica network, that is a glass, limits both the nucleation and the growth. So the crystallization is controlled by the diffusion of silica or the reforming of the silica network. And this is extremely slow because of the glassiness of the system. To illustrate in terms of the phase diagram what's happening during the synthesis, I'm presenting here a phase diagram that is the temperature as a function of the diameters of the nanoparticles. The green line shows the melting point from crystal to amorphous of the nanoparticles in solution as a function of their size, and it goes down, and this follows the Gibbs-Thompson equation. Now, when you are cooling down, when you pass this line below, the region of stability is the region of stability of the zeolite. But you can continue cooling from the amorphous melt without crystallization up to the temperature about Tx, that is the temperature at which the rate of nucleation is maximum, because the nucleation and the growth have the same speed. And above, between the purple or the pink and the green, the formation of the zeolites is controlled by nucleation. So there are big nucleation barriers, and then it goes downhill and it just grows. Below this line of Tx, now we show in green, in pink, what happens is that the nucleation becomes extremely fast, the barriers are lower, and as we are going down, first dominates the growth, but as we're going down, we start to approach the glass transition temperature. And when we approach the glass transition temperature, what happens is that both the nucleation and the growth become extremely slow. So the synthesis of zeolites is isothermal, so it's at a fixed temperature, let's say like 400, and it's like this arrow. You start with very small particles because they're polymerizing, and when they're polymerizing, they enter into the region of stability of the zeolite. But as they enter into the region of stability of the zeolite, first of all, they're too small, even compared to the size of a unit cell, and I'm going to address this in the next slide. And then they start to find that they want to form a zeolite, but they are already entering a glass. And what we interpret is that the crystallization of zeolites although it's a first order transition that should be discontinuous, appears like a continuous transformation from amorphous to zeolites, because occurs under these conditions of extremely high driving force, in which the barriers for nucleation are very small, and the times of nucleations are the same as the time of growth and the time of diffusion. So it's like a spinodal decomposition in which zeolitic units are appearing and trying to outcompete each other to transform into a large unit cell. This can be seen in snapshots of crystallization at different temperatures. In this particular case, I'm showing the pictures of crystallization for a nanoparticle that is 6.5 nanometers in diameter, that is a typical size of these precursors of zeolites, at 3 temperatures. The first one is at 640, is on the pink line. And what you can see is that under these conditions, the zeolites form quite beautifully. Actually, there is a lag time where nothing happens and suddenly a nucleus appears, the nucleus grows over all the nanoparticle, and you get immediately a very well-formed zeolite. And in this case, we're identifying zeolitic order in green and amorphous in blue. At the temperature that is below that, 550, that is already controlled by growth, the nucleation of the zeolite is pretty fast, but there are multiple nucleation sites. So what you see is many competing orders that all of them are zeolitic in green, but they're not forming a coherent crystal. However, if we wait more time, in this case it's only 650 nanoseconds, the real time would be much longer because we don't have chemical reactions. Then what you get is a 2 crystal nanoparticles. So these two are 2 pieces of crystals, one in one orientation and the other a different one. But these are perfectly crystalline in relatively small size times. However, if we get lower and sort of touching the glass transition temperature, what happens is that there is zeolitic order everywhere, and this zeolitic order evolves, but very slowly. After 2 microseconds, you still see a lot of disorder in the large scale, although there is zeolitic order in the short scale. I haven't updated this slide, but we have now 15 microseconds and it looks much more zeolite. It's becoming more of a zeolite, but I estimate that it will take at least 50 to 100 microseconds to really go to a perfectly well-defined zeolite like the one you see at 640. But these are times that are long for simulations, but they're really not so long in the synthesis. And actually, the synthesis of zeolite is very slow, and at room temperature, it takes more than a year to synthesize zeolites. Despite the disorder in these particles, what you can see is that the channels are already quite connected. And if you are familiar with the channels of the zeolite, that I'm sorry, probably you don't realize them, they look pretty similar to the channels of the zeolites already. So these particles that are halfway crystallized already have the catalytic properties and the structure of the channels, the porosimetry of the zeolite crystals. What we conclude is that because the critical nuclei at their conditions of synthesis, the last one, are much smaller than the unit cells that build the zeolites, that you have about 3 unit cells in some of these nanoparticles, then the zeolites start to form immediately. But that implies that the selection between zeolite polymorphs, the one that is the vexing question of how do they select, has to occur not during the nucleation, but during the growth around the excluded volume of the structure-editing agents. So what we think is that the reason why the templating mechanism is so powerful to predict which zeolites are going to form, despite not being related to them, looking like a continuous mechanism, what we think is that is because the polymorphs are deciding the growth, and in the growth, the silicates are going to form around the excluded volume of these channels formed by the structure-editing agents. That's how they template the channels. Now, finally, I would like to address in a single slide, what is the smaller size of the zeolite that you can form? Because I said that you are coming down from the monomers and you are entering the region of the zeolite at constant temperature, about 400 Kelvin. Under these conditions, you could form the nanoparticles already very early, but we don't see the formation of nanoparticles very early. So the question is, what is the smaller size? What we find by looking at this is that we can find the melting line, and then we can bring back the amorphous particles and cool them and find the crystallization temperature. And this, I told you before, is the pink line. These two converge at about 3 nanometers. And what we see is that for particles up to 3 nanometers, we can reconstruct by cooling, we can obtain again, crystallize the zeolite. Although already in 3 nanometers, what we find is a competition between the zeolite that we wanted and a more stable phase that doesn't have long range order, and actually in this case have 5-fold symmetry, that has a stability and doesn't melt until higher temperatures. So what we find is that for sizes that are very small, there is a competition in the order between the zeolite crystals and the periodic non-periodic order structures that compete. And this is the same also at 2 nanometers. And this finding that we have here for zeolites actually mirrors work we have done before in my group on the end of ICE1, in which we show that all the crystals, in that case we study ice, when you go to very low temperatures, you have the end of the first order transition, and then essentially you go into a regime in which you have sort of oligomers, and these oligomers are individual and they have structures that are dependent on the number of units. In this case, the 3 nanometer structure is different from the 2 nanometer structure and below. So we conclude that about 3 nanometers is the smaller, and actually this is the size very close to what have been achieved very, very recently, a couple of months ago in experiments, and we think that it's not possible to really go below this value. So in summary, I think I have covered briefly that it is possible to use molecular simulations with very simple computationally efficient models to provide insights on the different steps of synthesis of zeolites, the polymerization, the nucleation and growth. And I didn't show you, but we can also study the oriented attachment to form larger particles. And with that, we got many insightful results. First of all, is that we showed that the nucleation is non-classical from solution. So the oligomers do not already form when they're polymerizing the pieces of the zeolite. And these pieces that you see in the oligomers actually can be pieces of any zeolite. And later they're going to organize when they get into the nanoparticles into a small nuclei, and these small nuclei start to grow, and only then the polymorph selection is established. There are disordered pores already in the amorphous state, and these disordered pores probably are helping design and align the order of the pores in the final crystal state, because they're coming to, the crystal has to grow around the pores made by the structural aiding agent. Also, we found that the intermediate order does not arise, unfortunately, from a mesophase, although it could, but only at high temperatures that are not relevant for the synthesis. You don't need any other phase to help. What you need is to have temperatures, in the case of the synthesis of the zeolites, in which the nucleation is extremely fast, and what we're seeing is a slow crystallization inside the glass. So that's why it looks continuous, because there are multiple nuclei struggling to grow. And the polymorph selection occurs during the growth, not nucleation, and is templated by the excluded volume of the structural aiding agent, and the limiting size of the zeolite is very small, and this is the end of the crystal to melt transition, and below there are only isomers. And with that, I want to thank you again for sticking to my presentation. I'm looking forward to any questions that you may have.
So now we are open for questions. Someone of the attendants or panelists who wants to make. No? Okay, we have one from Miguel Ruiz. Let me try to give.
Yeah, okay.
I guess you can.
Okay, you can hear me, right?
Yes.
Thank you very much. So I had a curiosity, and just to make sure I understood. So I think I understood that the polymorph that is forming, it comes from this glassy structure that is choosing one of these forms. What I don't understand, I guess, is that you also mentioned how these organic molecules kind of direct the polymorph that you are gonna get. Mm-hmm. So I don't know. Is in the glassy phase, is percolated by these organic molecules, or what is it?
Yes, that's a great question. The reason why you don't understand is because we don't understand either. So that's why I didn't explain this part. So what we know is that the amorphous phase already has the channels, and these channels is because the silica is percolated by, let me get to a picture that shows them probabilities. Sorry, word job. The silica is already percolated by like in this case, the silica is percolated by these structure-aiding agents, and they have water inside, so they have a large proportion of these organics and structure-aiding agents. And the silica is building around them, so there's an excluded volume because of these organics. We have not yet studied a case in which we have two competing polymorphs in the same nanoparticle, because our system, the model we have is either we change the structure-aiding agent and it forms one polymorph, or it forms another polymorph. We don't have yet one that can answer directly your question of how do we go to one and the other. But what we know is that the critical nuclei, so the top of the barrier for nucleation, first of all, the nucleation barrier is a few KT, like 2 KTs or so. We also can use not only the models, but experimental data to show that. And the selection of the polymorph has been in the growth side when they're coming down and propagating. And in that stage, there are channels already. The channels are disordered. And what we see in the simulations that now are much longer is that as the crystals are very tiny and propagate, they reorder the channels, but always built around the structure-aiding agent. And different polymorphs, what they have is different size of channels and different connectivity. So what we expect is that when you have other polymorphs, for example, you don't go to this zeolite, but to AFI, the other zeolite, the channels are going to be more like hexagonal. So the order of the structure-aiding agent is going to reflect that already before crystallization. But we don't have yet the proof on that. And these are really very new results. So I cannot tell you exactly how are they doing the polymorph selection in the growth state yet.
Okay, but it's much more clear to me now. Like, thank you very much. And just for curiosity, are you gonna try to use like, you know, some other directing agent so that you try to get a polymorph that is not synthesized yet or something? Or?
Yeah, yes, we have done several, I show one example that is one zeolite, but we have done several polymorphs, and we can get polymorphs that exist and polymorphs that do not. Actually, the polymorph I'm showing here exists for metal organic frameworks, but not yet for zeolites. But then we have others that do exist for zeolites. It is possible. What we don't have yet to answer your question is one case in which with the same structure-aiding agent, you can go two ways, and by modifying slightly the conditions of synthesis, you go one to the other. That is what happens in experiments. Okay, so this is what I don't have to show you, but I would love to have. We want to work on that and get this competition.
Okay, thank you very much. It was great. Thank you.
Okay, another question? Valeria, I have one. If I understood, the size of the pores are very, very small, but have you considered if maybe including very small nanoparticles, I mean, when you create the mesophase and then try to stabilize, no, the size, or I mean the unit cell of the zeolites, and then when you remove the polymer, maybe try to improve better, I mean, in order to keep the structure or the zeolites.
Actually, we have not tried that, but we have been more on the goal of adding tails to this. So the particles, the pores, as you say, very small. They are less than 1 nanometer in diameter. The full particle that you see here is 6.5 nanometers in diameter. And this is the normal size of zeolite synthesis, are between 3 and 9 nanometers with an average about 6. So the zeolites form in these nanoparticles. And one thing that we have been looking at to stabilize intermediate states is to add a tail, essentially to go towards the mesophases are made when you have longer and longer tails. But at one point, if the pores, if you add tails, the pores try to become larger. But when the pores are larger, you cannot build the crystal structure around. That's why they end up being amorphous. So I think that there's a maximum size of the pore that you can make that is crystalline. But one area that we're interested in is on making hierarchical zeolites that are zeolites with different size of pores. The idea is to have large pores that allow reactant transport and small pores that allow the reactivity. So far, we have done, I mean, actually last week, sort of in a serendipitous manner, a zeolite that is some sort of a hollow shell that outside is a zeolite and inside is hollow. And so it's sort of around the lines that you are saying, to use different sizes to direct different scales. But it is possible, and actually is an area that is growing a lot on zeolites, to make hierarchical zeolites, to try to make small zeolites or zeolites that have large pores and small pores, so that you can separate transport and reactivity, because the reactivity requires very small pores, but the transport, of course, calls for larger ones. So this is something that we're working on.
Yeah, and another question by curiosity is, you said that it's better for catalysis if the nanoparticles, if the size of the nanoparticles is very, very small, closer to the 3 nanometers. So, I mean, by experimental way, it is possible to obtain that kind of size is very, very small. I mean,
yeah,
do you know if it is possible?
Yes, yes. So there is what people call nanozeolites or colloidal zeolites. They are typically in the order of 100 nanometers. So these nanozeolites in the order of 100 nanometers have been made for a long time. And they're coming from aggregation of these particles. But most recently, they are doing what they call few unit cell zeolites. And this paper that appeared in Angebandegimi like a couple of months ago shows for the first time the possibility of making particles that they say from 4 to 10 nanometers, but I think that the four is very indirect. They get from the X-ray, but they are getting images of particles that are like 7 nanometers. So these are the smallest that you can make. And the way they do, because you have to prevent the aggregation, is by using structure editing agents that are self-limiting, produce self-limiting growth so that they cannot continue growing. And so the new frontier is to make these nanoparticles and then prevent them from further agglomeration, because otherwise with Oswald ripening, they just become a large nanoparticle. And if you have this, then you can have agglomerations of these particles. And the advantage of the small particles is that all the pores are accessible from the outside without transport limitations. So they're getting to the size. So at this point, they got to something that they interpret to be 4, but what we say is that 4 is sort of the limit. They will not get lower, because below, the zeolites themselves become unstable. They collapse to form other structures that are more stable than the zeolites. That's our conclusion. So that they are reaching the limit already.
Okay, thank you.
Sure.
Another question? Someone? Anything? Someone else? No? Just maybe the last question. It's possible, for example, try to create like a zeolite structure, like in 2 dimensions, in order to have like a catalyst. I mean, it works like a catalyst, but in a surface.
Yeah. So what has been done is lamella. So you can get the zeolites to form a very thin, like 1.5, 2 nanometer thick layers. Imagine that it's like you cut a piece of the plane. You can make these as 2D structures. And the way they do it is with surfactants. So you have a zeolite that you know what is the structure editing agent to template the voids, but you also add a very long tail, and these long tails form these now lamella, and these on top of the lamella you can form the zeolites. We want to study that process too, because in that case what you have is multiple steps, and it's not clear whether they're ordering first and they're nucleating, or they're nucleating and then they're ordering. But you can make these nano zeolites that are essentially layers of, for example, silicalite or zeolites like this.
Yeah,
It's
because your focus is just in the gyro structure, but in
it has one. Yes, actually,
yeah.
we follow this one because in the beginning, I was convinced wrongly that mesophases would play a role in the nucleation of the zeolites, but then realized that they can play a role, but under conditions that people don't use them for synthesis. So we focus on this one because we could tune it, but now we are going to other materials that have one directional pores also.
Okay, excellent.
Okay.
Someone else? Another question? No? Well, thank you so much, Valeria, for your time, for your presentation, and you showed us incredible and very exciting results for zeolites. Thank you so much. So we are continue with our next speaker. Yes, Omar, are you there? Yes, I see.
Yes, I'm here.
Excellent. Just let me give a very briefly introduction of the next speakers. So now we have Omar Azzaroni. He's from Instituto de Investigaciones Físico-Químicas Teóricas y Aplicadas, okay, from the Universidad Nacional de La Plata, Argentina. Thank you so much, Omar, and to accept our invitation of this for this meeting. So the microphone is yours.
All right. Thank you very much. And I really appreciate your invitation. It's a real honor to be here in this meeting. Really enjoying these talks, wonderful talks. So today I would like to talk about one of the projects in our lab that is related to the use of solid state nanopores as signal transducing nanosystems. And the idea relies on the fact that we are using these nano devices for different purposes, and we're using nature as a source of inspiration. So first of all, we need to think about pores in nature. Nature exploits the versatility of nanopores, biological pores, in many ways. For example, controlling the transfer of ions or water, or for signaling different type of information. And also this conceptual framework used by nature was also exploited by biotechnology in different areas, like, for example, the creation of sensors, the creation of different structures for different purposes. So the idea of using biological pores as a source of inspiration for creating devices is something that is with us, with everyone dealing with these systems for a long time. There is something very interesting that I would like to talk about that is related to the work of Pierre Gilles, one of the creators of the terms of matter, in a quite old paper that is, the name was Flexible Polymers in Nanopores. De Gens stated in this manuscript, that in a physically constrained environment, interferential interactions and confinement-induced entropy laws can play dominant roles in determining molecular organization or chemical reactivity, which is something very interesting. In my case, I'm myself a chemist, and the idea of constraining something in a closed environment, in a nano-environment, is telling me that I can change the reactivity, which is something very interesting and very useful for different purposes. Then, talking about biological pores, one of the effects that is particularly interesting is the fact that biological pores, not every single biological pore, but many biological pores, they have the property of rectifying, the capability of rectifying the ionic transport. I mean, what's the meaning of this ionic rectification? The ionic rectification implies that if I just put this pore into a membrane and I polarize the membrane in one direction, I can measure one particular ionic signal. But then when I reverse the polarity of this membrane, the signal that I sense is much lower. Like in this case, you observe here that in the case of this calcium channel, when you reverse the polarity of this polarization, what you observe is that the current that you measure is different. That is what is called rectification. So with these things in mind, we started to explore the idea of creating artificial architectures that could be used to replicate these singular features observed in biological pores. To do so, we used solid state nanopores that are created by heavy ion irradiation. The way to do it is just we use a foil, a polymer foil that they are irradiated with a single ion beam, and then you just create a kind of puncture into this polymer foil, and then what you create is a track passing through this foil. This track is nearly between 5 and 15 nanometers in diameter, and the length of the track is the thickness of this polymer foil that is nearly 12 or 15 micrometers. We perform these experiments. These samples are prepared in Darmstadt and this Unilag. Someone might say, okay, but this is a quite sophisticated way to create nanochannels. And the answer is yes and no. Yes, it's quite sophisticated, but it's not far from the, let's say, our labs, because, for example, if someone working with millipore membranes for filtering solutions, those membranes are created using the same technique. In fact, this Unilag station, many times they just hire beam time for companies to create these membranes. That these membranes, they have the difference with our membranes, that our membranes, they have one single nanochannel. The commercial membranes created with this technique, they have multi-channels, multi-pores, but the technique is exactly the same. So once that we create this membrane with a single nanochannel, we just mount this this foil with a single nanochannel in the middle into a conductivity cell. That is a cell that is you have two reservoirs with electrolyte. You polarize the membrane and you measure the ionic current passing through the nanochannel. Pretty simple. Sometimes you need to change the geometry of these nanochannels, and the way to do it is not very complicated. You just create, because you are using a polymer foil, you just use a solution with the ability to etch one of the parts of the foil, and you create in one side of the reservoir, you use the etching solution, and on the other part of the reservoir, use a stopping medium or stopping solution. In that way, the asymmetric etching is creating a nanopore or nanochannel with a conical shape or asymmetric shape. The way to characterize the shape of these nanochannels is very simple. It's just by using an electrolyte deposition. You just create the negative of the nanochannel, and this ACM image that you see here is showing the negative of this nanochannel, in which you have a base which is nearly 500, 800 nanometers in diameter, and then you have the chip in which the diameter is nearly 10, 15 nanometers, but depending on the etching time, the tip could be larger, let's say 50 nanometers, 80 nanometers, 100 nanometers. It depends on the application, on the purpose of your measurement. It is interesting to note, a few slides back, I was talking about the ability of biological pores to rectify ion current. And one particular thing of these asymmetric nanochannels is that in the case that you have an asymmetric shape and you populate the nanochannel walls with charges, with fixed charges, what you observe is that rectification behavior. This is something that was observed several years ago by Alan Barr and Steven Felberg using glass nanopipettes. But then in this century, what we observed, like people like Susanna Sibi and Irvine, Then you observe that also in our type of nanochannels, these conical nanochannels, you also observe the rectification behavior when you create an asymmetric nanochannel and you put charges on the pore walls. In fact, the magnitude of this ionic rectification, because you are rectifying the ionic transport through this channel, is proportional to the effective charge on the pore walls or the nanochannel walls. So with this idea in mind, if you think about that we have a nanochannel and we can create charges on the surface, we will be able to create a sort of a nanofluidic diode that is able to rectify ion transport. So one of the first experiments that we carried out was to modify the pore walls with a polymer brush, in particular with a polyelectrolyte brush with a monomer unit that is bearing a polyprotic monomer unit. So in our case, we're using phosphate where you have two pKa's, and you observe here the difference between a monolayer, you just decorate the nanochannel with a monolayer of phosphate units, and then you create a polymer brush on top of it. So per each grafting site, instead of having one single phosphate unit, you have different phosphate units. In our case, we use per grafting site, we have 6 or 7 phosphate units. So increase a lot the surface density of fixed charges on the pore walls. And what you observe is a sharp increase in the rectification of this nanochannel. But you observe that these phosphate units are strongly dependent on a chemical equilibrium. So this chemical equilibrium is telling me that I can change the pH of the solution and I can change the effective charge of the nanochannel wall because I change the ratio between the population of a species with 2 negative charges or 1 negative charge. So one thing that we did is we were changing the pH of the solution, and we observed that in fact, when you remove the charges from this polyelectrolyte brush, what you observe is an ohmic behavior, a linear behavior, a linear current potential behavior, which is something that is what you expect when you don't have any charge on the pore walls. But as soon as you increase the pH and you start to ionize the monomer units, you start to observe the rectification behavior and you reach the maximum behavior above pH 10. One interesting thing that we observed, this has been done in collaboration with the Igares Lifer in Northwestern, is that if you compare the typical pKa's that you observe with this polyelectrolyte in solution, just by titrating this polymer in solution, and then you just run a sort of a molecular theory, this is a theoretical framework developed by Igal in Northwestern, you observe that the behavior that you observe experimentally for this polyelectrolyte confined in the nanochannel is completely different in terms of a chemical equilibrium. It's completely different from the one expected according to observations in bulk solution. And the reason is that we observe a strong pKa shift. pK1 is shifting from 4.5 to 5.8, and the pK2 is shifting from 7.7 to almost 10, 9.7. So that means that this is in line with the previous message by Pierre-Gilles Deschênes, in which strong confinement is changing the chemical reactivity, is shifting the chemical equilibrium, and we observe strong confinement effects in the chemical equilibrium of this polyelectrolyte brush confined inside the nanopore. And we explored this also according to the geometry, because we also performed some experiments using a different weak polyelectrolyte. In this case, we also perform experiments by creating polyvinyl pyridine inside cylindrical brushes. We did exactly the same thing, and what we observed is that when we have the polyvinyl pyridine, the apparent pKa in solution is 5.8. When you just grow this polyvinyl pyridine on a planar surface, so you increase the confinement from solution to a 2D surface, you observe by titrating this polyelectrolyte that the apparent pKa is 5.2. And then when you perform the same experiment, but inside a nanochannel, what you observe is that the pKa is also shifting to 3.7. So you observe the way that according to the genes, when you start to confine this polyelectrolyte, the pKa that is defining the chemical equilibrium is changing, is shifting. So by controlling, you can control chemistry by controlling the geometry in these nanoscale systems, which is something very, very interesting. Also, something that is an outcome of all the theoretical framework around these nanochannels is that not only the magnitude of the rectification is proportional to the surface charge density, also the magnitude and the sign of this charge that is resting on the nanochannel walls is defining the direction of the rectification. What I'm meaning is that according to the theory, the nature of the charge that we have on the channel walls is defining the direction. If I reverse the charge on the pore walls, we reverse the direction of rectification. So to do so, we synthesize a polyelectrolyte brush inside the nanochannel having sweet ionic monomer units. And monomer units, which are sweet ionic and they are also pH dependent. So according to the pH, what we have is a monomer unit bearing positive charges, and according to the pH, for example, by increasing the pH, we have monomer units bearing negative charges. And you observe here that you have this sort of nanofluidic diode that according to the pH, for example, at pH 2, you have the rectification in one direction, and then when you switch to a pH 10, you switch rectification in the opposite direction. So you have a ionic diode in which, depending on the pH that is operating, you are controlling the direction of the rectification of that ionic transport. You can perform similar experiments, and you can achieve similar functions by using different type of polymer units. One of the polymer units that we also explore is polydopamine layers, which is pretty simple to synthesize. You just expose these monomer units at the right pH to these nanochannels, and you decorate the nanochannels with this polymer layer. And then you can also use a sort of non-covalent functionalization approach, sort of supramolecular approach, in which you use some kind of polymer called amphipoles, in which you have an hydrophobic tail together with monomer units with different charges. And you can use an amphipole in which all this hydrophobic tail is promoting the absorption, the self-assembly on the surface, and then you expose to the solution these hydrophilic monomer units that, according to the pH, you can promote a positive charge or a negative charge on the nanochannel wall. And this is the result of these experiments, in which by using a non-covalent approach, you can switch, you can reverse the pH, and you can change the rectification behavior of this nanochannel. And because of this self-assembly of the polymer on the surface is very robust, you don't need to, let's say, perform any sophisticated chemistry or do any kind of preparative chemistry that is time-consuming, or you need highly trained people to synthesize the polymer. Just by simply dipping the nanochannel into this polymer, the polymer self-assembles on the surface of the nanochannel, and you can render this sweet ionic behavior in a rather simple way. So far I have described different ways to modify these nanochannels in a way to control the transport properties and to use these nanochannels as ionic diodes. So Now I will start to describe another way to exploit the behavior of these nanochannels, now by introducing different type of recognition sites or molecular recognition units inside these nanochannels, and how to use, for example, these structures or architectures as a sort of nanofluidic sensors. So the experiment is based on using a polymer, using the same approach that I described before. We use a polymer in which some of the monomer units were labeled with a ligand, which is called biotin, and the biotin has a strong interaction with the septabidin, acting as a ligand receptor complex. So the conceptual framework is described in the slide. The idea, the paradigm is just by decorating the nanochannel walls with this polymer, in which we expose these biotins, and then in the presence of streptavidin, the streptavidin should recognize this biotin, and something should happen. So what is the idea? Because the tip of the nanochannel is nearly 10, 12 nanometers. A few streptavidins, or the streptavidin itself, is behaving as some kind of biomolecular cork, you know, because as soon as the biotin is recognizing the biotin on the tip, it's acting as a cork. You have a strong size exclusion effect in the tip, and because of this behavior, this property, this recognition process, what you create is a sharp change in the effective cross-section of the tip, and then you affect the conductivity of the tip, and as a result of the recognition event, what you observe is a sharp decrease in the rectified current. And this is exactly what you observe here. When you have the behavior, the rectifying behavior of the nanopore in the absence of the streptavidin, but as soon as you put 1 picomolar streptavidin, you observe here a sharp decrease in the current because of this sort of biomolecular cork that is precluding the transfer of ions through the channel, and you have an 80% decrease in the rectified current. If you increase even more the concentration of the streptavidin, you increase even more the change in the current, in the rectified current. Someone in the audience might say, okay, but this could be, for example, done by simple fouling of the protein close to the tip, not due to the recognition event. And that is a good question. So we perform a set of blank experiments in which we not only use a much higher concentration, but we use a set of proteins which are quite sticky, like BSA, bovine serum albumin, 100 nanomolar, or using lysozyme, also 100 nanomolar. So when you expose this nanochannel to these two proteins at these concentrations, the rectified current decreases only 14 or 9%. So that means that in our case, with this, the previous experiments in the presence of streptavidin, the ionic current is in fact transducing the recognition event into an ionic signal, or let's say a sort of iontronic setup in which we're able to transduce the recognition event taking place on the tip of nanochannel into an ionic current. In the same way, we can decorate the nanochannel walls with other kind of receptors. And as a chemist, I like supramolecular chemistry a lot. And we decorated the nanochannels with crown ethers. These architectures are widely recognized for the ability to bind different alkaline ions, or even in this case, depending on the size of the crown ether, you're able to recognize, for example, potassium over sodium. So we did so. We decorated the nanochannels with this crown ether with the ability to recognize potassium, and you observe that in the presence of 0.1 molar sodium chloride, what you observe is the ohmic behavior. we observe here is ohmic behavior. That is a non-rectifying nanochannel. But when you change, you replace the solution and you use 0.1 molar potassium chloride, you observe the rectification. And the rectification takes place because the potassium ions that they are playing a role as carriers, charge carriers across the channel, they are also playing a role as fixed charges on the nanochannel walls. And they are playing a role as fixed charges because of this recognition, this binding, this strong binding with the crown ethers, they are attached to the surface. And as soon as they attach to the surface, they render the surface positive, and this positive net charge on the channel walls are triggering the rectification of the nanochannel. I have described a few examples in which the stimulus that we use is recognition, biomolecular recognition, or even ion recognition. Another stimulus which is particularly interesting to us is the use of electrochemistry. Why? Because we can change the state of a polymer or the channel walls by using electrons. Instead of using pH or a particular chemical species, we can use electrons or electrochemical potential to change the characteristics of the nanochannels, and in that way control their ionic transport through the nanochannel. So to do so, we create the nanochannels, which are first of all covered with a thin gold layer, because we are going to run electrochemistry into these nanochannels. So we need to create a conductive surface on the nanochannel walls. So after we decorated with the nanochannels, we coated with a thin gold layer, we electropolymerized polyaniline. It's a conducting polymer. The good thing about polyaniline is that polyaniline has 3 redox states, which in principle is giving me the possibility to create 3 different regimes in which each regime is associated to a redox state of the polymer, and those redox states can be controlled by electrochemistry. So here is the result in which, by changing the electrochemical potential that we exert on the polymer layer, we control the rectification of this nanochannel. And you can control the rectification in different regimes. Because you just generate an electrochemical conversion on the polymer layer induced by electrochemistry, you can also not only inject electrons, but you can take out electrons by controlling the electrochemical potential. So that is quite interesting, because you can reverse the change that you induced previously by changing the redox potential, by changing the applied electrochemical potential. And that is exactly what we did. Here you observe that the rectification factor, which is a sort of measure of the ability to rectify the ionic transport, can be reversed by changing the electrochemical potential. In other words, is reversed by changing electrochemically the state of the polyaniline on the nanochannel walls. One of the things that could be a little bit complicated, make things a little bit complicated in the previous example is the gold layer. The gold layer is okay, can be done, is reproducible, but it would be quite interesting if we just can put a polymer that could act as a conducting layer and also as a redox active layer. So one of the polymers with this ability is PDOT. PDOT is a polymer, it's a very interesting polymer, widely used in organic electronics, in which you can control the redox state by using electrochemistry. And it's quite interesting because by changing the condition at which the electrochemical potential that you exert on this polymer layer, you can have different states. You can have a state in which you populate the polymer layer with negative charges, and you can change the electrochemical potential in a way that you populate the polymer layer with positive charges. So this gives us the possibility to create a sort of pseudo-ionic behavior in this nanochannel in which the nature of the charge could be controlled by the electrochemical potential. And here are the results that were of our experiments, in which, depending on the electrochemical potential that we apply to this nanochannel, we have the rectification in one direction, in the opposite direction, and of course, you can tune the redox potential or the applied electrochemical potential in a way that you don't have any excess of positive or negative charges, and because you don't have any net charge on the pore walls, what you have is an ohmic behavior, a non-rectifying behavior. So by using PDOTs, a polymer that is widely used in organic electronics, inside the nanochannel, you create a nanofluidic device, a nanofluidic diode, in which you can change from rectifying to ohmic behavior, and depending on the applied potential, you can control the direction of that rectification behavior, which is very versatile. It's a lot of versatility around these systems. So here shows this, I'm showing that by changing the gate voltage, which is the applied electrochemical potential, you can change the rectification behavior quite nicely. It is also very interesting to know that we have two different mechanisms that they are concerted to some extent. What I mean is that we promote an electrochemical change in the polymer layer, and that change in the polymer layer is promoting a change in the transport through the channel. So you have one electrochemical process that is coupled to an ion transfer process through the channel. So the question is there any lag time between one process and the other process? They take place simultaneously? Well, here is one experiment which is quite nice, in which you observe that both processes take place almost at the same time. When you have electrochemical conversion of the PDOT layer, you observe immediately the change in the transmembrane ionic current. So that means that the possibility of using this polymer, this sort of architecture, you are able to tune the rectification behavior by using electrochemistry without any lag time. Both processes are occurring simultaneously. The same approach can be done by using a different polymer. In this case, we use polyorthoaminophenol, which is called POAP. We use exactly the same approach, and by using this approach, in this case, by changing the electrochemical potential, you can change from a rectifying behavior to a non-rectifying behavior. So by using the electrochemical potential, you can switch the rectifying behavior of this nanofluidic diode, or you can switch it off. So the switch on and switch off is controlled by electrochemistry in a very simple way. And once again, these processes take place almost simultaneously. I mean, you can change the redox potential or apply electrochemical potential to the polymer layer, and you immediately observe that behavior in the ionic properties of ionic transport properties of this nanochannel. You can use this sort of behavior, this kind of polymer architectures that you can electropolymerize on these nanochannels for different purposes. In the recent slides that I described, we use these polymer layers as a platform to change the ionic transfer properties by controlling the electrochemical potential. The good thing about these polymers, like in the case of polyaminobenzyl amine, is that these polymers, they show some affinity to different molecules of, let's say, biomedical interest. Because, for example, in this case, this polymer, which is called PAVA, there is a strong interaction with dopamine. So if this interaction with dopamine is changing the effective charge of the polymer layer, we can have a very simple platform to detect dopamine in the presence of a nanochannel decorated with this polymer layer. And this is in fact what you observe. We decorated the polymer channel with this polyaminobenzyl amine, and then we exposed this nanochannel to increasing concentrations of dopamine, which is a neurotransmitter. And what you observe is that the rectification is changing according to the concentration of dopamine that we expose the nanochannel. And we observe here that, in particular, this nanofluidic sensor is very sensitive at very low concentration of dopamine. Of course, you observe here that the behavior is close to similar to an isotherm. And the reason is, of course, you have a limited number of coordination sites on the nanochannel walls. So when at the very beginning, when you expose the nanochannel to the dopamine, you have many sites, but then when you start to populate the binding sites, you saturate the binding sites, and then the rectification behavior is not changing in a similar way. And that's the reason why you observe that there's a sort of isotherm behavior in the rectification factor. It's because you are saturating the binding sites on the nanochannel walls. But the same approach could be extended to other type of species, like borate ions. This is something that we have done this year, or in the case of adenosine triphosphate, ATP, that these experiments, these results were published a couple of years ago. So I hope you understood that all these behaviors, all the decoupling of these processes taking place into the nanochannels. And there are a few things that are quite important to understand our results. Is that in the case of a nanochannel, in particular asymmetric nanochannel, when we change the effective charge on the nanochannel walls, we observe a change in the rectified ion current. So I have discussed several examples in which we can use this platform as a biosensing strategy. So what we have done a couple of years ago is, why not we don't create a sort of enzymatic assembly in which the enzymatic process can change the effective charge of the nanochannel, and because of these concerted functions associated to the enzyme, the nanochannel walls with the charge, and the ionic transport, we could use a sort of enzymatic nanofluidic sensor. So the experiment is quite straightforward, it's quite simple. We decorated the nanochannel with polyalyl amine, which is a polyelectrolyte. The polyelectrolyte, a cationic polyelectrolyte, which is a weak cationic polyelectrolyte. We assembled this polyelectrolyte on the nanochannel. The nanochannel was exposing carboxylate groups. So on top of that, we assembled urease. The urease is an enzyme that, in the presence of urea, generates or degrades the urea, leading to an increase in the pH. The enzymatic reaction of the urease in the presence of urea has as a result a pH increase. So if we have all this enzymatic process taking place into a nanochannel that is decorated with polyelectrolyte, this local change in the pH will change the protonation state of this weak polyelectrolyte sitting on the nanochannel walls, and these concerted functions should have an impact on the ionic transport properties of this nanochannel. And that is exactly what we have done, and that is exactly what we have observed. Here, you can observe that the rectification factor of this nanochannel, the rectification ability, is strongly dependent on the concentration of urea. And the reason for that is that when we increase the concentration of urea, we enhance the increase in the pH. And that's a strong enhancement in the pH increase is changing the nature of the charges on the nanochannel walls, and is changing the rectification properties. This change is very fast. The enzymatic process takes immediately inside the nanochannel. You observe here that as soon as you just inject 3 millimolar urea into one of the reservoirs close to the tip, you observe a sharp change in the rectified ion current. And you observe that rectification of this nanochannel has a nice dependence, a quite predictable dependence with the concentration of urea. So that means that we are creating a sort of enzymatic ion trailing transduction that is mediated by these concerting functions of enzymes and polyelectrolyte, weak polyelectrolytes inside the nanochannel. It's a way to create a nanofluidic biosensor. You can change the concentration of urea, and of course, when you change the concentration of urea, you also affect the pH change. And if you affect the pH change, you can reverse to a different concentration, a different population of effective charges on the nanochannel walls, and you can reverse this process depending on the concentration of urea. So now I'm close to the end, and I would like to talk about some results that were published this year, in which the concept was we were able to use these nanofluid elements, these nanochannels, to detect proteins, small analytes, or small molecules. Would it be possible to use these nanochannels, these nanofluidic sensors, to detect a virus, for example? So the idea started a couple of years ago when we had the idea to detect human adenovirus. So by using aptamers are segments of DNA, oligonucleotides, that by a selection process, you're able to detect, to identify segments with a particular affinity to a particular ligand, like for example, or a species, like in the case of a virus. Here you observe that if you have a virus that is, for example, deactivated, it's non-infectious, and then you have a virus that is infectious, these two viruses, of course, they have differences that these oligonucleotides are able to identify. So that is a very good thing, because we have now a recognition element that is able to recognize the virus in the active state. So we decorated these nanochannels with these aptamers. We exposed these nanochannels, these nanofluidic sensors, to these increasing amounts of adenovirus, and you observe that when you have no aptamer, or you're exposed to a virus that has been deactivated, that is non-infectious, you don't see any change in the rectification behavior. So the nanofluidic doubt is the transfer properties are the same. They don't see what's going on around this nanochannel tip. But as soon as you replace the solution, and you replace that solution by a solution containing the active virus, the infectious virus, what you observe that when you increase the concentration of the virus, suddenly you observe that this nanochannel is telling you that something is going on the tip, something is going on in the transfer properties, is detecting, is transducing the presence of this virus, because this recognition of this virus close to the tip is changing the characteristics of the tip, and the change in the characteristics of the tips has a strong influence on the transfer properties. Of course, you may say, okay, but you should try with different active viruses, for example. Yes, of course. For example, we have tried with infectious virus, with non-infectious virus that they were deactivated by using chlorine or UV lights. And also we have explored this aptamer decorating this nanochannel using different types of viruses like a murine norovirus. And you observe that this nanochannel is very specific to adenovirus. And the specificity is given by the aptamer. And the sensitivity is given by the characteristics, the transport properties of these nanochannels. And of course, we're struggling with this pandemic across the globe, across the world. And we started with human adenovirus in 2019, I guess, the end of 2018. And then in 2020, we explored the same platform with SARS-CoV-2, with COVID, to detect COVID. And we did exactly the same thing, with the difference that we just had to run a different aptamer. We have to run the right aptamer that could be able to distinguish discriminate between active and non-active SARS-CoV-2 in a way that we should be able to detect infectious virus and not infectious virus. And we perform exactly the same experiment. And here you observe that in the case of exposing this nanochannel to this infectious SARS-CoV-2, you have a well-defined signal that is increasing according to the concentration of the virus in the sample. I would like to say that here that we tested these samples with these nanochannels with real samples, with saliva samples containing the virus. So this, in particular, in the case of SARS-CoV-2, we ran these measurements with real samples. You observe here, in the case of when you correlate the concentration that you get in the case of the sensitivity, we observe here that the nanopore, the sensitivity is nearly the same that you observe with typical assays, like for example, the luciferase assay, which is something very good. It's telling us that this platform is very sensitive. Sorry. Okay. As a summary and also as an outlook, I hope you have an idea of our work related to the use of nanochannels, not only as nanofluidic devices for different purposes, for controlling ion transport, like, for example, ionic diodes, but also the use of these architectures as biosensing platforms in a way that with the right design of the nanochannel walls, you can use these platforms as nanofluidic sensors or nanofluidic biosensors. I would like to acknowledge all the people involved in these activities and all these experiments and all these results, and not only lab members of our lab, the Soft Matter Laboratory at INIFTA, but also colleagues that were former members of our lab and now are working in different institutions, and also colleagues and friends from different parts of the world, like in the case of people at GSI in Germany, in Gallien Western of YILU University of Illinois at Urbana-Champaign. Also, I would like to acknowledge CONICET, who is paying my salary, and also the Argentinian agency that is providing the funding for experiments. Also, financial support from the Max Planck Society, the von Humboldt Stiftung, and the DAAD is greatly acknowledged. We're thankful to them for that. And thank you all for your attention, for all your questions. I'm hoping to answer soon. Thank you very much.
Thank you so much, Omar, for your presentation and your incredible and amazing results about nanochannels. Now we are open for questions from attendees or panelists? Let me check. Okay, I have a question. Well, I have several questions, but one of them is, it is possible to have like enantioselectivity. So, I mean, if you can put some kind of molecules and try to make a separation of the enantiomers. Have you tried to do that?
We didn't try those
Possible
experiments.
to do that?
No, it's a very good question. I mean, we didn't try those experiments, but I do know that the group in China is working in that direction. The group in Beijing is working in that direction.
Excellent. Okay, cool. Ivan?
Yes. Hi, can you hear me?
Yeah,
Yes.
of course.
Hi, Omar. Oh,
Nice to meet
great.
you.
Nice to meet you too. Congratulations for your amazing talk.
Thank you
It's
very
a
much.
very experimental, interesting experimental work. I have a couple of questions. How do you measure the PK in confinement? Because as you show us in your presentation, it can differ a lot from the bulk. And the second question is, have you experimentally tried to test this rectification behavior near an interface between immiscible liquids, for example, water and oil? Because, for example, if you have a cell, you have water outside and you have a lipid inside, for example. So you have two different dielectric constants. I wonder if you have performed some experiments in that way. And the third question would be, how do you determine the charge of SARS-CoV for your experiments?
Well, the first question is, it's not trivial to estimate the PK inside the nanochannel. This is a very, very important question. The way we do it is in collaboration with the Gales Lightfair in Northwestern. They run molecular simulations of the system. I mean, we provide them with all the experimental information that they require. I'm talking about the type of polymers, the degree of polymerization, the dimension of the nanochannel, all the asymmetric shape, and I mean, all this stuff. And they have this molecular theory that is able to replicate the experimental observation, what we observed. And according to these results, the theoretical results that reproduce our experimental results, we infer that the apparent PK is the PKs that I reported in this presentation. But it's not like in the case that you titrate in bulk solution. No. With this data that I have described here, in the case of the nanochannel, these data are taken from the theory, but the theory that has been used as a theory to fit the experimental results.
I see.
The second one is if you use different medium, different media. Yeah, that is interesting. I mean, we didn't. I mean, I do know that we try with a different solvent, like create like a liquid interface. You create a rectifying interface for sure. The thing is that we didn't try that, but we did try something that is also triggering the rectification is using polyvalent ions. When you use ions of different charges from in both sides in different reservoirs, this asymmetric characteristic of the reservoirs is also translated into an asymmetric behavior. And in the case of using a different solvent, for sure, you will observe rectification properties affected. And the other question is about SARS-CoV-2.
Yes.
Well, in the case of the SARS-CoV-2, what we observe is that, well, we didn't estimate the charge of the SARS-CoV-2. But what we did in those experiments is to use, I mentioned, slightly at the very beginning of the presentation, that we, in many cases, we work with nanochannels with a tip diameter close to 12, 15 nanometers. But depending on the application, depending on the purpose of our experiments, sometimes we need to increase the diameter. So in our case, for example, I will use, for example, something here. We have, this is the tip of the nanochannel. So we want a diameter close to the size of the virus. So the way that we created this architecture, this biosensing architecture, is by increasing a few tens of nanometers the diameter of the tip in a way that the virus has a comparable size to the tip diameter. So as soon as the virus stick to the tip diameter, you have two effects. One is that you decrease the effective size of the tip, but also we know that this nanochannel is charged. So when you increase the charge because of the aptamer and you change the size of the tip, you have an increase in the rectification. You have a variation in the rectification. And this is also manifested when you have a size or an object that is comparable in size to the tip of a nanochannel. This is the first part of the answer. The second one is, I mean, how are you sure? I mean, how sure are you that, I mean, you are sticking that virus to the tip? And the reason is that we perform those experiments with other viruses that we had the same opportunity to be hanging around close to the tip and close the tip, and you don't observe that behavior. So you need the aptamer to stick to the SARS-CoV-2 or the adenovirus, depending on the aptamer, to create this sharp change in the tip characteristics that is ultimately translated into the ionic behavior or transfer properties of the nanochannel.
So it's a combination between selection and charge. Is that right?
Exactly. Yeah,
okay.
Exactly.
I see. Great. Thank you very much, Omar, for your talk.
Thank you.
Nice meeting you.
Yeah. Likewise.
Hi.
Hi, Francisco.
Okay.
Yes. Sorry, Julio. Can I talk?
What do you mean?
Your microphone is mute, I think.
Hello?
Julio.
Can you hear me? Okay. Hi, Omar.
Hi, how are you?
Following the doubt of Ivan, I was wondering, in the case of this SARS-CoV-2, the charge distribution on all the surface of the capsid, meaning basically the proteins that are on the surface of the virus, is constant, meaning is always the same for all the capsids of SARS-CoV-2, or are they vary depending on, I don't know, the way they form, the self-assembly that they have when they are on the presence of cells?
Well, I think it can depend. I mean, it would depend also in the case of the variant of the virus, for sure. But in our case, the main difference is not, I mean, the difference or the strong behavior that you observe in the rectification is not about the charge on the virus. It's about the change in the charge on the nanochannel tip. And the charge in the nanochannel tip is provided mostly by the aptamer. Remember that the aptamer is a DNA segment, oligonucleotide. And the virus is acting as a massive cork trying to decrease the effective diameter of the tip. And the combination of these two effects is promoting a sharp change in the rectification.
So as long as you have this virus of this size and with some charge, you will detect something.
Yeah, and as long as you have the right aptamer, you will, I mean, in principle, physically, that's the bottom line. That's okay. But the thing is that to confer selectivity to this nanofluidic architecture, you need to find the right aptamer to reach that goal.
I see. Okay, thank you.
Very welcome.
Someone else for question? No, I have another question, Omar, about the nanochannels when you control it using electrochemistry.
Yeah.
Do you think, or I was wondering that it is possible to capture one kind of molecule, for example, CO2? I mean, you can capture using one kind of charge and then remove it, changing the charge from positive to negative, or vice versa, or another kind of molecules. I mean,
it's doable. It's just, what you're talking about is exactly the same concept that is commonly used in the case of conducting polymers for electrochemically stimulated release of a species. So you can use this polymer to absorb, like a sponge, any kind of chemical species, and thereby changing the redox potential or the electrochemical potential, you just create a condition in which this chemical species is released. That could be done. It's doable.
Okay, thank you. So, someone else? No? I guess the last question. For example, I know that you have a prototype, no, in order to sense to make a biosensor for SARS-CoV-2. But if you want, for example, if you commercialize these biosensors in order to make like a, you know, like a test for people or for the water or air, I don't know, it's really expensive to make this kind of materials in order to make like I don't know, dozens or hundreds of these tests.
It's a very good question. Yeah, I mean, it's quite a typical question, because when you show the station at UNILAC in which the samples are created, the members are created, people are a little bit scared about these samples because they think that they should be very, very expensive. But the thing is that they are not expensive. And the reason, I mean, to explain that is that if you go to the lab and, I mean, if you just buy from Wattman or Millipore these 200 nanometer filters made from polycarbonate, that polycarbonate membrane is prepared in exactly the same stations. These companies, they just buy bean time from in France, Russia, Germany. In some cases, they have even smaller equipment without requiring such sophisticated infrastructure to create these samples. So in my opinion, it wouldn't be very, very difficult to get access to these membranes, and they shouldn't be very expensive.
Okay, well. Okay, thank you so much, Omar, for your talk. Very, very interesting.
Thank you very much for the invitation.
And we are follow your research because it's so interesting. So now we, I guess it's time for break, for a coffee break. So we'll back in approximately 20 minutes. I don't know if Francisco or Victor has some announcement.
No, we're okay.
Okay.
No.
Well, we can take the time if someone has some question for our speakers, for Valeria, or maybe for Omar, for another kind of, and if they have time to answer the questions.
Julio, just to remember to the audience that we have this Gather Town application. If you want to talk, to meet with somebody just like individually, you can use that application. The link is in the chat.
Okay.
So that's another option if you want. And of course, the debate with the posters are also online on Twitter.
Okay. Thank you, Francisco.
Thank you.
Yeah, actually, thank you, Valeria. Thank you for for your presentation and to be here.
Very nice presentation, Valeria.
No, I love yours. So this was great.
Thank you very much.
And we hope to see you soon in a presential way.
Yeah, I'm going now. I have to drive to the office because I have to go and teach my class.
Yes.
So I will catch up later in the afternoon. Thank you.
Bye bye.
Great.
See you.
See ya.
See you.
Perfect. Thanks, Omar. Yeah, actually, if you have time, I have another question for you.
Please go ahead.
Excellent. So yeah, for example, in the case, there is like a magic size of the diameters, or depends of the proteins or the virus. So I mean, you can control the diameter of the cone, no, that you are making for the sensors. So I mean, it's related with the angle, or you can, how you decide the size of the, I mean, the diameter, the length of the pore.
Well, you have these two factors: the length of the pore of the nanochannel is mostly provided by, is given by the thickness of the foil. And in some cases, I mean, some people try to work with the shorter channels. Shorter channels means that you are working with thinner foils, and thinner foils, you have a problem that is mechanical stability. And because we are very interested in using these architectures for biosensing purposes, one key aspect is the mechanical stability. So let's say that the thinner foil that we use is close to 12, 15 nanometers. So that makes nanochannels that they are in length, the length of a nanochannel is close to 12 to 15 nanometers. That's regarding length. As to the tip size, it depends on the etching time. I mean, when you increase the etching time, you start to increase the tip diameter. When you are dealing with small molecules, of course, you are planning to use small tip sizes. But one thing that is quite important, that is probably the main part of my presentation, is that when you want to recognize a particular analyte or a particular chemical species, you need to, let's say, functionalize. You need to dress the nanochannel walls with any particular architecture. Let's say you have to do some interfacial nanoarchitectonics inside the channel. So you need to make some space for it. So the way to do it is you think about, for example, any particular interfacial architecture that you know that is responsive to any particular species. And you know that there is some complexity about creating this architecture. And then you start to think about increasing the diameter of the chip in a way they have room, enough room for creating this architecture. That is quite important. I mean, the answer seems quite trivial, but experimentally that sometimes you start to modify the nanochannel, and sometimes, for example, postdocs in our lab or students say, okay, I did modify the nanochannel, but now I observe that the nanochannel is occluded, it's closed. Because you started to modify the nanochannel, and when you start to increase the sophistication of the architecture that you create in the nanochannel, the chip diameter is increasing because of the size of the architecture that you put inside the channel. So the way to do it is, okay, so you need to start again and start with a nanochannel with a chip diameter that is slightly bigger, in a way that the final size, after you put all the stuff inside there, is close to, let's say, 10 nanometers.
Okay.
I have another question, if is there time?
Please.
Yeah, sure.
Okay. Omar, as you shown us in your presentation, the ports can be as small as a few nanometers in the case of molecules, as dopamine, but it can be also very large, as in the case of SARS-CoV. How relevant are hydrodynamic interactions in both limits?
Oh, that is a very important question. Well, in the case of having the experiments with the virus, they are not very critical, let's say. But in the case of the opposite direction, they can be quite critical, because you have two effects that they are coupled. Because when you start to decrease on the tip size, you start to increase. You magnify all the rectification effects, but you start to increase the resistivity of the nanochannel, and you also start to increase all the effects that is caused to, for example, solvent viscosity, pre-concentration of a species close to the tip. You start to observe the magnification of different effects that you don't observe when you're working about 10 or 20 nanometers. So the outcome of all the convolution of all these effects is when you just try to design a nanochannel that you think that you have a super rectifying behavior, and when you run experiments, that behavior is not that enhanced, superb as you thought, and the reason is that you have all these effects that you are neglecting when you were working about 10, 20 nanometers, and when you start to decrease the tip diameter, you have all these effects together. So this is something that we didn't quantify, but experimentally we observed them. So we care a lot about the tip diameter in a way that we are able to work in a regime in which the resistivity is not playing against us. We want to play in a regime in which the resistivity and all the transport properties are playing in our favor.
I see. And coming back to the SARS-CoV-2, in your slide, I understand that you were distinguishing between infectious SARS-CoV-2 and non-infectious. Is that right?
Yeah, that's right. Yeah.
Okay. And so non-infectious SARS-CoV-2 molecules have a difference in charge with respect to the infectious ones. Is that right?
Well, it's not only about charge, it's about the architecture of the virus. When you have the virus that for some particular means, it is deactivated, for example, exposing the virus to UV light or exposing the virus to chlorine, you change part of the architecture, the outer architecture of the virus. And then what you use is an aptamer that is able to discriminate slight changes taking place in the outer environment of the virus. And you use that in your favor to discriminate between active and inactive viruses.
I see. So you use the charge only to move, for example, the molecules through your pore.
Well, in principle, the charges that we use to create the signal is the ions that are in the solution. In the case of the virus, the contribution to charges, if you consider the size of the virus, if you consider the electromigration of the virus because of the potential that you apply,
yes.
If you think about in terms of transport coefficient, that would be very, very, very low, because you have probably you have some charges, but it's very big, so it's not changing anything, because in addition the concentration of the virus in the solution is very low. So the main signal is generated by the transport of potassium and chloride.
Okay.
So that's the main signal. Then because of the changes that are taking place close to the tip, the transport of these two carriers, potassium and chloride, is changing. And that is the signal that you detect in your device.
Okay,
that's why
okay.
you use the term, that's quite a good question. That's why we use the term iontronic measurement. It's not because we just want to create a fancy word. It's because you have the signal is created by, of course, you detect it electronically, but that electronic signal is originated by the change in the transfer of ions. That's why we call it iontronic.
I see. Yeah,
it's not
very
like
interesting.
For example, a real behavior.
I see. Great. Thank you very much.
Very welcome.
Ivan,
sorry.
Sorry, just one thing quickly. Ivan, so you continue as a chair?
Yes.
Excellent. So I left for a few minutes. Thank you.
Right.
Continue, Paco.
Yeah, so I was following your discussion, and it was really interesting for me the question that Ivan said about the effect of the hydrodynamics. But at the end, as I imagine this case of the SARS-CoV-2 is at the end is a colloid of the order of 100 nanometers, where around this colloid, this sphere, you will have several proteins of the order of 10 nanometers, right? So this effect of electrohydrodynamics, I think, is a competition between hydrodynamics transport and the ions also. Therefore, I think hydrodynamics is important even in bulk, because if you put obviously if you put a flow, these flows will be modified by the colloids, meaning by the virus. I don't know at which point, for example, if you have a distribution of charge around the virus, this will give you a suspension of virus with a really stable, with a lot of stabilization among the virus because of the charges, right?
Yeah, I do agree with that. What I'm talking about is that the effect of this, let's call it the electromigration effect, in the case of the virus, is not the decisive step to create the signal, because the virus is very diluted and is not also affecting from the point of view of the transfer coefficient. But of course, I mean, the virus is also, you can think of the virus as a colloid, and that's for sure, because they have all the elements to be considered a colloid. Yeah, for sure, I agree.
Thank you.
All right. Are there any further questions? Okay, well, if there are not any further questions, I would like to thank you again, Omar, for your really nice presentation. And we can come back at what time, Paco? At 11:20? Is that right?
Sorry, what's your question? At which time we will start again?
Yes.
In 6 minutes, something like that.
In 6 minutes, okay. Okay, anyway.
All right. See you soon.
All right. Thank you very much, Omar. See you.
Thank you, Omar. Really nice talk. Thank you.
Thank you.
Hi, Yuk. How do you do? Oh, your microphone is.
Yes, I just had to unmute myself, but good morning for you. So
Yes,
nice to meet you in this conference. And well, the program of this conference is extremely interesting. Many nice talks listed on the program. but I have to say, well, that I have to watch the recordings later because I just arrived from the classroom, was teaching this afternoon, and well, that's for several afternoons. But so the program is really interesting.
Great. Thank you very much for accepting our invitation. I think Paco is one of the organizers. He has a question. Go ahead, Paco.
Yes, nice to meet you, Chuck. Since you is here as a panelist, can you put Miguel Ruiz also as panelist if they want to try to check if their slides are okay? And I don't know if Cecilia will be around.
Oh yeah,
but at least Miguel is here.
Okay, yeah, that's a good question. Let me upgrade him. Yeah. Now Miguel is a panelist too. And I think Cecilia isn't arrived yet.
Okay.
Okay. So,
hi, Miguel.
Hi, Miguel.
Hello, good to see you. So could I check 1 sec the slides just to make sure that I know how to?
Sure, go ahead.
Okay. 1 sec. Because sometimes I have to share my whole screen, and sometimes I have to share the presentation. So okay, can you see it?
Perfectly.
Now you see the full screen, hopefully.
Yes.
And do you see my pointer if I do this?
Yes.
Okay, great. That's everything I wanted to check. The only thing, okay. Okay, great. Thank you very much.
Sure, no problem.
Okay.
Do you want to check your screen?
Yes, that would be great. I will start sharing my. Let me check. So you see, I guess, one screen shared, and now you see my slides, right?
Yes, perfectly.
Okay.
How do you pronounce Waningen? Is that right?
Yes. So my name is Jouke Dijkstra, and I'm assistant professor in Wageningen. Well, Wageningen is hard to pronounce. It's actually, I think, for many people a check to see whether, well, to find out what the level of Dutch is. So it's internationally very hard to pronounce. I think also there are many international students in Wageningen, and well, I think many after they stayed here for 5 or 6 years, well, still find it challenging to pronounce the name of the city correctly. But so Wageningen is the pronunciation, but well, Wageningen is sometimes used in the international context. So
I see. I will do my best
then
to pronounce it.
It's always challenging with these with conferences to pronounce the names of speakers and of universities correctly. That's the challenge for the chairs. Well,
I see. Yes, you're right.
Shall I stop sharing first, or shall I keep my screen shared? What do you prefer? I can stop.
No, I think it's okay. Let me see if I can see. Yeah, you can. If you want, you can keep it, because we are starting in, I guess, 1 minute. Well, a little bit, a couple of minutes. All right, it's 11:21, so I think it's a good time to continue with the conference. Welcome everybody to the second session of the conference. Our next speaker is Professor Joke Dijkstra. He works at the Wageningen University, and he is interested in electrochemical engineering with a focus on ion separation processes, ion and electron transport in porous media, including membranes and electrodes, interfacial phenomena in nanoporous materials, electrical double layer formation, chemical interactions, and Faraday reactions. And on behalf of the organizing committee, I thank you for accepting our invitation. So please, you can start with your presentation.
Thank you. Thank you. Thanks to the organizing committee. Thank you for the invitation, and also thank you for having this conference with this very interesting program. I have to say that I will watch several lectures later on after the conference, but fortunately many lectures are recorded, and that's really nice. So good morning, everybody. Good afternoon, good evening. I know that, for many people it is 11:20 in the morning, very nice time. I'm in Wageningen in the Netherlands. It's 6:20, also a very nice time to join a conference, and currently still at the university. That's also nice to have this lecture, this conference talk after lecture this afternoon. Would really like to use this possibility to explain you more and to discuss more about ion transport phenomena and chemical reactions. And I think the combination of these two is very interesting in nanoporous materials for environmental engineering. So nowadays there's a lot of focus in environmental engineering on membrane-based or electrochemical processes. Well, and in all these systems, we have to deal with membranes for which ions are transported. We have often porous electrodes, activated carbon electrodes, or other electrodes. And it's all really interesting to describe and to discuss the phenomena that occur, including the transport and the chemical reactions. So why do I like to work on the fundamentals of ion transport and electrode processes in electrochemical cells? Well, as you can see, in electrochemical cells, we often employ membranes in which ion transport phenomena are important. And these processes, they can be used for several applications. They can be used to generate electrical energy, to store electrical energy, or to generate product streams of higher energy. That is, for example, the case if you desalinate water, or if you use electrosynthesis processes to produce chemicals like hydrogen. So if we understand the fundamentals, if we understand the ion transport phenomena in these cells, well, we can use it for several applications that are all very relevant nowadays. For example, electrodialysis and reverse osmosis. There's a big demand for effective and efficient water treatment technologies, but also for electrochemical cells to store energy. Well, why is it that interesting to work on these technologies in the field of environmental engineering? Well, of course, we have the application, for example, for water treatment or water desalination. There's a lot of big societal demand for these systems, but also scientifically, it's very interesting. Firstly, we often deal with complex water streams in which we have many components that are present. And amongst these components, we have amphoteric ions. These ions, for example, like phosphate and ammonium, but also organic ions, their charge is dependent on the local pH. So in this cell, we may have strong pH gradients, and the charge of these ionic species is dependent on the local pH, and therefore also the transport is, and the transport rate is dependent on the local pH. Furthermore, there's a strong focus on nowadays on resource recovery, can be energy, but also on resources that are present in these complex water streams, like, for example, the recovery of phosphate or ammonium. And well, that's why these processes are also very interesting, because you want to understand how you can recover these resources. So if you look at these systems, these electrochemical systems for environmental engineering, you could say, well, we have water entering the system, we want to produce clean water. Furthermore, we want to recover valuable or harmful chemicals. Well, we want to recover valuable chemicals and we want to remove harmful chemicals. We want to evaluate the energy input, or we want to harvest energy. And in these cells, we employ porous electrodes that can be used for ion adsorption, that can be used for chemical conversions. And we want to study in these electrodes, well, if these are porous, we want to study these processes inside these electrodes. We want to describe and understand the transport of these amphoteric ions, but also of other species, across these membranes. And well, this combination is extremely interesting, and it is very interesting, especially because we develop strong pH gradients, and all these processes are affected by these pH gradients. So if you want to understand these systems, want to work on these systems, we always have to come up with a joint description of the cell, where we evaluate ion transport in these different components, and where we focus on the complex water stream. And by that, we can then evaluate ongoing, well, acid-base equilibria and ongoing changes in the water chemistry that are pH dependent. Well, in these electrodes, we have, besides the transport of species, we have interfacial phenomena, electro-interfacial phenomena between ions and the charged media. So this will always result in a coupling of transport and well, electro-interfacial phenomena in a theoretical description. And that's very nice. And these are the topics, there are several topics related to this that I would like to discuss today with you. First of all, I would like to elaborate on these electrode processes and the difference between capacitive and Faradaic processes. I want to talk about ion transport and how we can understand this based on simple membrane characterization experiments, and that we can also use these to predict selective transport, for example, of sodium over potassium, the other way around, or nitrate over chloride. I want to elaborate on the transport of amphoteric ions, and I will show that based on a theoretical description, we can also find situations where we actually have proton shuttling across anion exchange membranes or bipolar membranes. And we'll discuss the topic of transport numbers with you. And to conclude this talk, I will show you how we can couple these ion transport processes to electrode processes, and that these can also cause, well, that we can observe very strong pH gradients in cells where we have only non-Faradaic processes. And I will show and illustrate how these phenomena result in a new innovative electrochemical process for boron removal. I will also explain the relevance of this. So today's talk includes fundamentals, but it will always relate it to technologies or to applications in the field of environmental engineering, because I think that this is quite interesting to discuss. So let me start with the first topic, Faradaic versus non-Faradaic processes. Often this is, I would say, can be a highly debated topic, and well, sometimes it may be unclear what a Faradaic process is and what a non-Faradaic process is, and about specific processes there's a lot of discussion. And I believe that this division that I will illustrate and discuss now of electrode processes in the categories Faradaic and non-Faradaic is very useful. So a Faradaic process is in general a process where we have an electrode, electrons arrive at the electrode, ions arrive, and there is a Faradaic process running, and ions leave again. So the electrode, and that is very important, does not store any ions or electrons. Everything that enters leaves again. So only ionic species that enter this electrode, they leave again. That also means that the structure of the electrical double layer does not change in steady state operation. So in steady state operation, we have a stable structure of the electrical double layer, which is the electrode. So important examples are fuel cells, lead acid batteries, water electrolysis, or reference electrodes. But we also have non-Faraday processes. And in non-Faraday processes, there's a big difference. There we have electrons that arrive in this electrical double layer, in this electrode. And ions, they can enter and they absorb, they associate to the electrons. But the products, and that's the big difference with Faraday processes, do not leave the electrode. So the electronic charge changes in time. And the electronic charge in the electrode changes in time. And this is a division that has been, made also by important scientists in the field of electrochemical engineering, but that I, together with Maarten Biesheuvel, Slawomir Pohada, elaborated upon and discussed in a recently published paper, actually not recently, last year, updated on arXiv. So you can download it, and we discuss this in more detail, but we will also discuss it today. And perhaps the first question is, why do we want to distinguish these processes? Well, first of all, we have different phenomena. That means also we have different physical descriptions. For example, related to the electrode potential, whether this is stable or whether this gradually changes when you apply a constant current. And so it is important to distinguish these processes because there are different phenomena and there are different physical descriptions. So you have to know which description to pick, and therefore you have to distinguish these processes. Well, how do we distinguish? Well, we do not need to know what happens inside the electrode. So many people could argue, well, you have to know, you have to understand this, you have to check what really happens. Based on this, you have to, then you you can define these processes. Well, we say you do not have to know exactly what happens inside the electrode, but you have to analyze how the electrode responds to a current or to a change in voltage. And that's what we do. So for a Faraday process, what typically happens if you have a current and if you apply a step change to this current, you will see that after applying the step change, well, your voltage increases and there's first some change, but after that you arrive at a stable value and you operate at a stable value. Then when you would apply another step change, again, the voltage increases and you arrive at a new stable value. So when a steady current is applied, the electrode potential does not change in time. In non-Faraday processes, when you have a step change in the current, well, then immediately you see that you have an increase in the voltage and your voltage keeps on increasing. So the response is still dynamic. So when a steady current is applied, the electrode potential keeps on changing in time. So if you use this, and if you look at these differences between Faraday and non-Faraday processes, you find that Faraday processes can be typically described using a steady state current versus voltage curve, a polarization curve. And for non-Faraday processes, you characterize these based on charge voltage curves. So then you typically evaluate the charge that is stored as function of the voltage, or you evaluate the voltage as function of the electrode charge. So that these are the typical characterization curves that you have for these different processes. So you can divide these processes in different categories. So you have, for Faraday processes, you have typically processes that are steady state, fuel cells, lead acid batteries. You have corrosion processes, also in steady state. You have redox flow cells. And if you go to the non-Faraday processes, the capacitive processes, you have typically the processes where you have porous carbon electrodes that you employ. You have capacitors, of course, but you have also physical intercalation materials where the structure of the electrode is changing in time. Lithium-ion batteries are an important example. Redox active intercalation batteries. So you have different processes where you really see a change of the structure of the electrode over time. Well, as I said, you can characterize these processes using different curves, different curves. So for Faraday processes, you typically use current voltage curves, polarization curves. For non-Faraday processes, we look at charge voltage curves. So then I want to continue. So after discussing this, I would say fundamental difference between capacitive and Faradaic processes at these electrodes, would like to continue with ion transport phenomena that are typically occur in porous media, in membranes, and where we want to characterize these membrane materials in such a way that we can theoretically nicely predict how which ions are transported and whether you have selective transport of one ion over the other in case you have complex mixtures. So let me start this topic by illustrating electrodialysis, an electrodialysis process for water desalination, where we have feed water entering the system and we apply a current or voltage, and by that we desalinate a certain water stream, or we partially desalinate a certain water stream. And between these electrodes, we have stacked ion exchange membranes in order to make sure that we have diluate compartments for which where we actually remove salt or ionic species, and we have concentrate compartments where the concentration of ionic species increases during operation. And nowadays, there's a lot of focus on, it's important to understand whether we can use this electrodialysis process also for the selective transport of certain ionic species. And for example, in greenhouses, and it's a important topic, there's a lot of focus on selectively removing, for example, sodium over potassium. If you have a technology where we can really remove sodium and where we keep potassium in solution, that would be really interesting. So if we can predict this selective transport, for example, of sodium, and also use this to optimize this, for example, of membrane materials, that is really fruitful. So in order to do this and in order to understand this, we elaborate on different transport mechanisms: migration, diffusion, and advection. And we want to understand how these mechanisms contribute to selective transport. Well, how can we describe ion transport across these membranes in these cells? Well, for that we can use the Nernst-Planck equation, where we evaluate the flux of an ionic species as function of concentration gradients, potential gradients, and also advection. So we include and evaluate advection, diffusion, and migration. And we want to evaluate this ion transport across ion exchange membranes. And for that, we set up for every ionic species a mass balance equation that evaluates the concentration change over time as function of the derivative of the flux, in which we insert the Nernst-Planck equation, and furthermore, we assume local electroneutrality. And this includes all ionic species and the chemical charge of this membrane material. Furthermore, we evaluate at the membrane interfaces, so at the interface of the membrane with the solution, we evaluate the Boltzmann equation, where we relate the concentration of ionic species inside the membrane to the concentration in the bulk solution as function of a donor potential that is developed at this interface, but also as function of several terms, like the volumetric excess term, that can include volumetric effects, and we'll come to that later, or chemical affinity, for example, a chemical affinity of certain ionic species to the membrane material, And we can also include molecule-molecule interactions. So in this Donnan equation, we can include several phenomena that are of relevance and that occur at this interface, besides the Donnan exclusion effect that we will always evaluate. For now, I will, for this electrodialysis example that I will discuss now, I will focus on Donnan exclusion and chemical affinity, and then we'll forget about volumetric excess effects and molecule-molecule effects. And I will show you, because we have then a model that includes several relevant parameters, diffusion coefficients, includes the water flow, and it includes this chemical affinity term of ionic species with the membrane material. I will show how we can characterize these membranes such that we find relevant values for these parameters that we include in the model. So we have the parameters, the diffusion coefficients, and this chemical affinity term, and I will show you how we can find values and how we can use this. So to determine this chemical affinity, we do experiments where we have solutions in which we have the target ion and where we evaluate as function of the concentration of this target ion in the bulk solution, the concentration inside the membrane. And we can do this for sodium and for potassium. And we also did this for mixtures. And what we find, and I think this is really interesting, these values that we determine for this chemical affinity based on individual ion experiments. So based on experiments with the target ion, only the target ion present. These values we can also use to predict the affinity of membrane materials in mixtures. So if we have mixtures with sodium and potassium, we can use the same affinity values that we determined in individual solutions where we had only the target ion present. So we can determine then, and we also found that we have a higher affinity or selectivity of these membrane materials towards potassium over sodium. Furthermore, we have to determine the fusion coefficients, and determining the fusion coefficients of ionic species inside the membrane material is a challenge, an interesting challenge. You would think it would be, we also thought it is simple, but what you find often in literature is if we determine the membrane conductivity or the resistance of a membrane material as function of solution, the concentration inside the solution, you often find these typical curves where at lower concentrations in the external solution, the membrane conductivity is much lower. That is what you would typically find, I think, also what you determine experimentally often, but this is not correct. It's also weird because, well, we know the chemical charge of the membrane material, and we also know that the chemical charge of the membrane material has to be compensated by ionic charge. So the fact that at what you will find experimentally perhaps, that at these lower concentrations in the external solution, the membrane conductivity is much lower, does not make sense. And what I really like is this paper recently published by Diaz and Kamchev. They also evaluated the ionic conductivity of ion exchange membranes. They evaluated this with different techniques, and they really nicely showed it also experimentally at these lower concentrations, the ionic conductivity is still high. So at these lower concentrations inside the external solution, you still find high values of the ionic conductivity, and that's also what you would predict based on theory. And that's a really nice result. So we use this, and we use the this approach where we only look at data points of the conductivity at higher concentrations, and then we determine the diffusion coefficients inside the membrane. And we find that typically the diffusion coefficients of sodium and potassium inside the membrane are about a factor of 50 lower than the values in free solution. And this also relates nicely to a plot figure 7.2 in the physics textbook that I wrote together with my co-author Maarten Biesheuvel, Physics of Electrochemical Processes, where we evaluate the membrane charge density and the membrane reduction factor, and where we also show that the membrane reduction factor, the reduction factor of these diffusion coefficients inside the membrane, is strongly dependent on the membrane charge density. And for these highly charged membranes with a chemical charge of about 6.5 moles per liter, well, we find typical values in the order of 40 or 50 to reduce the diffusion coefficients inside the membrane. So this is nice. Well, we can do this, and we can also use then these values to predict ion transport of multi-component solutions, so of sodium and potassium. And based on these values, these diffusion coefficients, these affinity terms, we can nicely predict the fluxes of ionic species across these membranes. And that's very nice. We are nowadays also looking at possible extensions. And one extension is to include size-based effects. And that would all be very nice if we can do this nicely, to include size-based exclusion effects, because then we can also use it to describe and evaluate the removal of larger components, for example, with electrodialysis and reverse osmosis. Well, then you may wonder that why I mentioned these two different technologies, completely different technologies, electrodialysis and reverse osmosis in one sentence. Well, what I believe and what we also show in this paper that has been recently published on Archive and has also been submitted for review to another journal, is where we that you use the same theoretical approaches for both reverse osmosis or nanofiltration and electrodialysis. So for all these membrane-based technologies, you can use the same theoretical approach. And a PhD student at Wetses and in Wageningen is nowadays using this and also considering the size-based exclusion effects to evaluate the potential of micropollutant removal of larger organic components that you don't want to have in your treated water with nanofiltration. And the aim is to describe this all theoretically and also to predict this. Well, and to do so, well, he is characterizing all these organic components based on three important criteria: the molecular weight, the solubility, and the pKa values. And then the aim is to predict, well, their removal performance of these pollutants with these technologies, with membrane-based separation processes. Well, now I will continue, and I want to show you how we can also evaluate the transport of amphoteric ions. And these are very important, especially in the field of environmental engineering. And we'll illustrate this using the example of a carbonic acid, bicarbonate, and carbonate group of species. So what we can do, we can set up a mass balance equation for each individual ionic species, evaluating the concentration change over time as function of the derivative of the flux of this species, plus the production term of carbonic acid, of carbonate ions due to acid-base equilibria. Well, what we know, if we do this and if we set this up for all these individual ionic species, we have three different gamma terms. These are then the production terms due to acid-base equilibria. And what we know is that if we sum these gamma terms, we arrive at a value of 0, because, well, we there is no production of these species due to acid-base equilibrium reactions. And this allows us to sum these mass balance equations, and then we arrive at one overall mass balance equation that includes the concentrations of carbonate ions, bicarbonate ions, and carbonic acid ions. And then we have this one mass balance for, you could say, the family of carbonic acid species. Well, we can extend this with equilibrium conditions, and that's what we do, acid-base equilibrium conditions. And then we arrive at a system of equations that does not include the reaction kinetics, and that's very nice. Because then we don't have to evaluate the reaction kinetics, we don't have to know individual rate constants, can assume local equilibrium between these acid-base species. And we do this, and we did this to model, for example, the transport of amphoteric ions in electrochemical systems. And we'll not go into detail, but here we evaluate a cell that is used to produce acetate, an organic molecule, from CO2 by applying, an electrical potential difference between electrodes. And the aim is to understand the transport of acetate from the cathode in this cell towards the middle compartment where you would, where you aim to up concentrate this. Well, to evaluate this, we evaluate the transport of several species: acetate, acetic acid, the carbonate ions, sulfate, bisulfate. We evaluate this all in different groups. And I look now only at the transport across the anion exchange membrane because we found some interesting phenomena there. And I will show you now on the next slides how we evaluate this. And we evaluate this using the transport numbers. And you may often read about transport numbers or transference numbers. Well, transference numbers are defined like this. We include the diffusion coefficient and the concentration of an ionic species, but this only works and is only a useful metric if there are no concentration gradients. Well, in our systems, you typically have concentration gradients because you want to up concentrate or you want to desalinate. So then this metric is not very useful. Then you can use, the transport number, where you evaluate really the local flux at a specific position over the current density, the ionic current density, and that's what you express then. So we use the transport numbers a lot, where you have the contribution in reality, considering concentration gradients of an ionic species to the local, ionic current. Well, if you evaluate these transport numbers over the anion exchange membrane, there are a few very interesting things that you observe. Because firstly, you observe that we have transport numbers, negative transport numbers, at the interface of the anolyte in this case, but we also have transport numbers higher than 1. In total, if you would sum all these transport numbers, you still arrive at an overall transport number of 1. But you can have negative numbers, you can have positive numbers higher than 1. What you also see is that actually bisulfate basically is transported across this anion exchange membrane in one direction. Sulfate is transported in the opposite direction. And net, this means that we are basically shuttling protons across this layer. And we'll explain a bit more about this in the next few slides. Also, we observe that at the interface with the anolyte, the charge is carried by other species than at the interface with the catholyte. And that's also very interesting. And what we find is that we can relate this to the local pH. So at the anolyte, we have a local pH around 2, and the catholyte around 7. And we mainly see that the protons are shuttled by the group of amphoteric ions that has a pK value close to the local pH. So at the interface with the anolyte, this is bisulfate sulfate. At the interface with the catholyte, this is bicarbonate. So then, based on this, you can propose for these systems a proton shuttle number, like which group of species shuttles the protons across the anion exchange membrane. We also found that we can evaluate ion transport across a bipolar membrane. And what is very interesting is that you often think, well, we have a bipolar membrane. That means that we have water entering a bipolar membrane on both sides. And then at the interface of this anion exchange layer and a cation exchange layer, we split water into protons and hydroxide ions. That's often assumed with these bipolar membranes. But that is not completely true, because here we found that across this anion exchange layer in this membrane, basically bisulfate and sulfate ions shuttle or transported. And it also means that we are basically shuttling protons across this anion exchange layer in this bipolar membrane. So although people would think, well, in this anion exchange layer, we only have the transport of hydroxide ions, we basically find we can shuttle protons across this layer if bisulfate and sulfate ions are present. So you have then an effective transport of protons across the anion exchange and cation exchange layers inside this membrane. So that also means that amphoteric ions should really be considered in theoretical descriptions of these bipolar membranes in order to understand transport process as well. That's what we show in this, this work. Well, then I want to go to my last topic that I would like to cover today, the coupling of transport processes and electrode processes. And we'll show you how this can result also in non-ferrite processes in very strong pH gradients. And I want to do this, and I want to illustrate this using an example of a technology where we have two porous carbon electrodes, capacitive electrodes, that can be charged in order to absorb ionic species and can later be discharged in order to release this again. And we use a cell for which we flow a solution. So there's a water solution, a feed solution entering, that flows through the electrodes. We apply a certain voltage and then we absorb, electrosorb ionic species inside these electrodes, and we remove them from solution. And in order to describe these processes, we have to evaluate the transport of ionic species in micropores, in larger pores for which ions are transported, and we absorb and we evaluate the absorption of ionic species, electrosorption, in electrical double layers formed in the smaller pores, in the micropores. So in the micropores, we electrosorb, we really store the ionic species. In the micropores, we have to transport. So micropores ion transport and acid-base equilibria. In the micropores, we have electrosorption, we have chemical equilibria, and we evaluate two different types of surface groups, chemical surface groups that are present. But I will not go too much into detail here, but I want to show you that again, to evaluate this, we use the Nernst-Planck equation, extended Nernst-Planck equation, and we evaluate local chemical equilibria between amphoteric ions and also between protons and hydroxide ions. And interestingly, we find during operation, theoretically in these kind of systems, extremely strong pH gradients. And this is just to illustrate this. So we have the anode that's placed upstream, the cathode that is placed downstream, and you see you have, you see the dotted, the black dashed line, that is the local pH, and you really observe close to this interface between the anode and the cathode, a strong pH increase. Well, this is very interesting, and you may wonder whether we could use, and that was what we were wondering, whether we could use these pH gradients, whether we could do something meaningful with this. Well, and that's what we did, and that resulted in a new innovative electrochemical process for the removal of boron. That's also how I will illustrate this. I will use this example. You can also use it for other species like arsenic or micropollutants, organic micropollutants. And this was published, and I have to say it wasn't published today, but published last week. You can on the in PNAS project, nice paper on electrochemical removal of amphoteric ions, and we'll show you how we can use this for the removal of boric acid in a bit. And this was a project that was conducted together with Technion, a group of Matthew Suss, and two PhD students, Amit and Eric, and Maarten Biesheuvel at Wetses and Huub Heinaerts in Wageningen. So we worked on this. This was really a joint effort between amongst 3 institutes. And as I said, I will show you and illustrate to you the case of electrochemical boron removal that is possible with this new design where we have water flowing through 2 electrodes and where we utilize local pH gradients for specific purpose for boron. Well, why do we care about this? Well, in conventional seawater desalination with reverse osmosis, we have a challenge. We have seawater entering. We have desalinated water that we produce with very low concentrations of salt, but unfortunately, boron is still present in the effluent of this reverse osmosis installation. So boron is present in seawater, and it is not completely removed by reverse osmosis. And as boron can be detrimental to plant growth, you really want to remove it. So we need something there in order to increase the removal of boron. And for this, we use this idea of this electrochemical cell that we could use as a post-treatment step kind of electrochemical water polishing step after reverse osmosis. And to do this, we need very high pH zones because we need a high pH in order to dissociate boric acid and to electrosorb it, because boric acid is often present in uncharged conditions at pH values below 9. Boric acid is mainly present in uncharged form. That's also the reason why it's that hard to remove it. And in this process, we show how we can use these pH gradients in order to dissociate it, get it in the charged form, and then adsorb it. And what we find is that we can effectively remove boron in this cell at this interface with the anode. So where we have this high pH. And that's what I want to show you. So we evaluated this, we studied this cell, this design for cases with different electrode orders. We studied cell designs with a cathode placed upstream. We found very limited boron removal. We also studied it with the anode placed upstream. Then we found high values of removal. And then we were wondering why. Well, if you place the cathode upstream, we find low pH values in the anode, but we need high pH values because these high pH values, these are required to dissociate boron and to adsorb it. Well, if you use the cell and we place the anode upstream, we have this high pH front in the anode, and there we can remove boric acid effectively. Well, we validated this also experimentally, and it's very nice to see that in general, data and theory show a nice match. So then you may wonder, why do we actually observe this pH increase in the anode cathode configuration with the anode placed upstream? Can we also understand this? Can we understand this based on what we find? Well, if we look at the results, we find that in order to increase the pH, we have to adsorb protons. So we have to make sure that we adsorb protons. And that's something we can do in the cathode. So protons must be adsorbed in the cathode. And for that purpose, a low sodium concentration is required, because otherwise you would adsorb sodium ions. And therefore we place the cathode downstream, because then we reduce the concentration of sodium chloride first, and we are at low concentrations. Then we start adsorbing these protons, and then, well, we have water dissociation, and we produce hydroxide ions, and we produce that many that we have some hydroxide ions, or a large part, that propagates upstream, that diffuses upstream. And then we arrive at these high pH fronts in the anode, and there we can adsorb boric acid effectively. So are we there? Well, not yet, because we have typically situations where we have influent concentrations close to 0.4 millimolar, and we want to have more than 50% reduction, because the WHO set a guideline of effluent concentrations of 0.1 millimolar. So there's still room for improvement, and that's what we are working on now. And we'll skip this part, I will not go into detail here. I want to show you that we do these evaluations of the local pH as function of the salt concentration and also as function of the flow rate. And based on this, you can identify the right conditions at which you have to operate the cell in order to have high pH values in the anode that are of importance to remove boric acid. I want to conclude this part of the talk with this overview of amphoteric ions that are especially interesting for these, for this process. And what you see here is you see for different amphoteric ions like arsenic, phosphate, and acetic acid, in which regions, pH regions, these species are charged and in which they are not charged. And well, especially for arsenic-free, you find that at high pH values, they are charged, at low pH values not. And that these are also challenging to remove with conventional membrane-based technologies. And for these type of ionic species, this process may be very interesting and well, useful. So in conclusion, this shows a new chemical-free technology for boric acid removal based on rational design And we show that we can use extreme pH gradients, that we can have these, and that we can also use these for the removal of amphoteric ions like boron. So in today's talk, I covered many topics: electrode processes, ion transport, transport of amphoteric ions, coupling, transport to electrode processes. And these topics are also covered in a book I wrote together with Maarten Biesheuvel, and you can download this free of charge on this website, this link. So if you're interested in these topics, and you want to learn and understand how you can model these, how you can theoretically describe these nicely, I would like to invite you to read this. And lastly, I would like to thank my group, my PhD students in Wageningen and at Wetses in Leeuwarden, who are working on these important topics. And of course, my co-author of the book, Maarten Biesheuvel, and also the collaborators in this boric acid removal project. And then after that, I would like to thank you. So to conclude this talk, I would like to thank you for your attention. Thank you.
Thank you very much, Professor Juk. It was a very, very interesting presentation. So we have time for questions from the audience. Are there any questions? I have some quick questions. Yeah. Do you think it is possible to use the technique that you propose to remove boron? I mean, to clean water in which you can have larger molecules like macroions?
Yeah, well, I think that that is possible. Of course, if it comes to the ionic species and to the size thereof, you have to consider more things. So you have to consider also size-based effects in the adsorption process. Well, you also have to evaluate and we have to make sure that the pore size is optimal for these larger ionic species. But I think in general, there is there is a potential also for larger organic components to be removed with this process. I would say this process is really mainly interesting in case pH gradients are of importance for the removal process, and that is for species where you actually have to get them in the charged form in order to electroabsorb these effectively. So I think that is the core of this process. I mean, there has to be pH gradients have to be important or of importance for the removal process. So for these ionic species where this is important, to get them in the local, in the right form, in the right charged form, well, there's potential.
I see. And I wonder if you have heard about blue energy?
Yes, definitely.
Okay. And would you say that is a Faraday or non-Faraday process?
Well,
or
I
in
would
which
say,
limit?
I would say so. I think so. Blue energy, I would say, is a mixing mixing process. So it's the reverse of electrodialysis. And I would say that at the electrodes, typically in these systems, you have Faraday processes running, because there you have at the electrodes, on the electrodes in blue energy, you have an electrochemical process that is running. But I would say the process itself, we call this a mixing process. And then, what happens at the electrode? Well, if you use typical electrodes that are often used, these are then Faraday. But sometimes you can also have capacitive electrode processes in blue energy. I think that is then what they call, with a fancy name, cup mix. So then you operate this with capacitive electrodes that are charged and discharged.
I see. All right. Let me see if there are more questions from the audience. Okay.
Yeah.
Well, yes.
No, I think
okay.
it was so extensive talk, many topics covered. So
yes, yes.
Questions.
Okay, we need to move with the schedule. I want to thank you for your very didactic talk. It was very, you were very didactic in your exposition, and thank you very much for accepting our invitation.
Thank you for the invitation. I will stop sharing my screen.
Great. Okay. Thank you. So our next speaker is Professor Cecilia Nogués. She works at the Institute of Physics at the National University of Mexico. She has received several awards. For example, she's member of the Mexican Academy of Sciences, and she's interested in optical properties of nanoparticles and surface-enhanced spectroscopies, optical and electronic properties of surfaces, and Casimir effect in real materials at the nanometer scale. So your microphone is, let me activate your microphone. Yeah, okay.
I have already. Thank you.
Sure. So the microphone is yours, Professor Cecilia.
Thank you very much. I would like to thank the invitation and your passion all this time. Today I will talk about more in solid state physics, and I will talk about two-dimensional materials. And let me just to share my presentation. And okay, I guess you are already looking at that. Well, yes. As Ivan said, I am at the Physics Institute at the National University of Mexico in Mexico City. And I will talk about how the physical properties of two-dimensional van der Waals heterostructure depend on the angle between the crystallography of these systems. Okay, so let me just to start with a brief introduction. Well, this kind of materials, probably you know, we can have a lot of different two-dimensional materials like graphene, hexagonal boron nitride, and different decalcogenides. Actually, there are more than 1,800 different materials that can be the candidate to have these two-dimensional systems that can interact by van der Waals forces. And in this way, well, we can think to try to make different devices by coupling different kind of materials with different properties. And the main idea of this system is to try to find the stability and to have uniform properties in this kind of systems by this vertical stacking with these interactions that can easily modify the crystallography, let's say, of these two-dimensional systems. The other idea is to try to find some synergy between materials, and so we can have mixed properties, individual properties, and of course also we can have new properties with this combination of materials. And adding to these systems, we can have new degrees of freedom, like is the angle between the two materials, and we can now control this angle, and now we can find and modify these novel properties in these particular systems. Actually, there are some new observations. For example, like optical activity, superconductivity, and other kind of topological effects, just by looking at these different angles between the two layers, which are vertical stacking. And of course, this allows us to think in potential applications, like to localize and transport energy, with the charge carriers, to think in, for example, to control the heat transfer, because we can think in these topological systems, or to have specific sensors, because now we have we can play with a lot of degrees of freedom, so we can think in different things. I look at that. I have something in Spanish here, but don't worry about that. It's sometimes happens. For example, we found with the collaboration with another group in the United States that this chiral, for example, if you have graphene and graphene, and you can manage the angle between the angles, between the systems, and you can play and find different chirality. That means that you can change or rotate the polarization of light in a very, very small space, just by changing the angle between the two layers, between the graphene layers. This is some new phenomenology found in these systems. And as I said, you can find, for example, as a function of this angle as well, that you can change from an isolator to a superconductor by looking, by playing also with the carrier density and the temperature of the system. As I said, also, we can create different topological channels just by stacking this. And I will talk a little bit more about these findings that we have. No? Okay, so just to remind you, graphene is a two-dimensional system. This system is a crystalline system because we have a periodicity along the two-dimensional plane, in a plane. So we can define, just for completeness, we can define two vectors from which we can reproduce all the two-dimensional system. And in each unit cell, this is a unit cell, which is shaded in blue, we can identify two atoms. So this is the real space. This is then the reciprocal space, the one which is in the middle. And the reciprocal space is also an hexagonal space, like this one, like in graphene. And we can now define the irreducible brilliance zone, which is defined by the gamma point, the K point, and the N point. And this is the band structure that we can find in this kind of systems. And in graphene, particularly in graphene, we know that this is a semi-metal system where in close to the K point here, okay, and the Fermi level, which is here indicated with 0 in the 0, we have a linear dispersion of the bands. Usually we have a quadratic dispersion of the bands, but here we have a linear dispersion of the bands, and that means that the electrons in that point behave like ultra-relativistic particles and satisfy the Dirac equations. Okay, so this is more or less let's say the resume about this. No, let me just move. Okay, yeah. Okay. What is interesting in graphene? Well, that the the velocity, the momentum of these electrons, no, close to the K point, are independent of the mass, are mass independent, no, because they are relativistic particles, and the mobility of that electrons is very large as compared with the usual system. However, one problem with the graphene is that we don't have a gap that we can control, for example, the transition, the electron transitions, which is very, very useful to create different optical, electron-optical devices. And this is why we want to, for example, to control the vertical stacking and the angle between the two layers composing this vertical stacking in order to try to have a gap and to control this kind of systems. So we can have the typical vertical stackings and let's say the ideal ones, where, for example, we can have that this red, remember that we have two different kind of, not different, but we have two atoms that compose the unit cell. But in this vertical stacking with an angle equal to 0, okay, we can have that this red atom is above this red and the blue one is above this one, and we call this the AA stacking. And also we can have the stacking, which is typical in graphite, for example, that are also these two-dimensional systems, but a lot of them, where, for example, the red atom is in the middle of the hexagon here, or the blue one is as well in the middle of the next hexagon. However, we can think that we can have these two layers which are rotated between them. And now, for example, we can have unit cells that repeat in the two-dimensional space. We can identify these unit cells with these numbers. That means how many of the original lattice vectors A1 and AB we need to repeat the unit cell. And now what is interesting is that all these vertical stacking are composed, for example, with this AA, no, this is shaded in green, stackings, or for example, AB stackings, these ones, no, or BA, no, if we can think in the different, in their reciprocal or the imaging stacking in this way. And the way that we have these local regions of this stacking, for example, depends of the angle, no? Each of these numbers, no, are identify an angle of the interlayer angle between the two graphene layers, and now we can have different number of stackings, no, and that are represented with this AA, AB, and so on. No? Okay, so we can have this spatial uniform two-dimensional films. Now the people can control these atomic systems with micrometers and even centimeters, 1 centimeter, like there are people doing that. And now we have the other two-D graphene, for example, or 2D film. And now we rotate. And these are more or less how they look. And these are angles different from 0. And these are the unit cells that we can have, no, in these cases. I just want to show you. And these arrangements and these unit cells and these atoms can be seen in electron diffraction for example. And we can see that, for example, as smaller is the angle, we will have a larger supercell, no, that composed by both layers, and the number of atoms that compose these unit cells are also larger. Okay, so that represents a challenge if you want to understand the physical properties, because now, for example, the electronic bands will increase a lot. Let me just to remind you, for example, how when you do a supercell, how the bands are folded into the reciprocal cell, and how the bands looks. For example, this is the 1-by-1 unit cell of graphene. I remember that we only have two atoms. This is the unit cell. This is the typical band structure with a linear dispersion here, okay? And now we have exactly the same unit cell, but now instead to use the smaller one, we use a 2-by-2 unit cell, no? I mean, we have 2 times in one direction and 2 times in the other direction. We have exactly the same system, but now we can look that these bands are folded, and the physical properties are exactly the same. However, to understand the electronic properties and the electronic behavior is quite difficult to do by looking at these folded bands. And the same look happens with 3-by-3 and 4-by-4. And what I'm showing this, because remember that now we have these 2 layers that when they are rotated construct a supercell. And now to look and to understand the physical properties, the electronic properties in this case, are quite difficult to extract from this. So what we want to do, or what we did, is to do a band unfolding. For example, in a larger unit set, you have a smaller reciprocal space, and you have this band folding. And what we want to do is to look at the band unfolding, okay? And then to look what happens with interaction between the cells, okay? So for this, we developed a methodology. We used a standard, let's say, DFT program, DFT code, which is available for everyone, called Siesta. This DFT program uses an atomic-like orbital space set, okay? And what we did is to develop a method to unfold the bands and to try to understand what happens. So what we do once we have the electronic band structure of these complex systems, these supercells, what we do is to project the band structure, that means the eigenvalues and eigenvectors, eigenfunctions, at the same reciprocal space that the primitive unit cell, for example, of the graphene, on the presence of something else. And then we orthonormalize the system with a method. We identify the atoms. We try to understand how we are extending the cell, and how and how to reproduce, for example, the original unit cell by an extension and rotation of the system. So we do a post-processing of this. And what is interesting here is that we calculate by looking at this normalization of the band structure, the wave functions. We can assign a spectral weight of the band structure. I mean of the wave functions after, for example, of the presence of the second layer. That means that we can say we are looking how much of the original system we can reproduce on the presence of a second system, and from this we can extract the physics of the system. So the band unfolding process is known. For example, the people have done this by just looking at the expansion. Don't look at the equations. The main idea is that we have this expansion, and we can try to understand or to reproduce the original cell, okay? But what we have introduced here is the rotation of the system, okay? Not only the expansion of the system. And for example, we can have, this is the folded band structure of graphene. And by looking by these spectral weights that tell us how much of the original or unperturbed wave function is as compared with the new wave function, we can, for example, reproduce the original band structure. Let me just show you some examples. So we have, for example, this is a reciprocal space of the red one. This one, no, is the reciprocal space of the graphene. Now we consider an expansion of this unit cell, which now give us this reciprocal space in green. And this is for example, the irreducible Brillouin zone for the supercell. And this one in red is the reciprocal Brillouin zone of the graphene, of the original graphene. So we can calculate the band structure of this expansion of the system. And this is the band structure. And now we can recover the band structure of the original graphene by looking at these weights of the system, of the wave functions. And for example, here, that means that all these which are in red are the projected, no, or the unfolded band structure of the system that, well, we reproduce everything because it's just the unit, the original graphene system. The same we do by rotating this. Now, for example, you can see that the graphene is rotated as compared with the unit cell. No, now there is a rotation. Again, we can calculate, for example, the bands in this supercell, and then we can project and obtain the weights of the system in this unit cell. And again, we reproduce exactly the same band structure as the graphene one. This is just to show you that we can do that very easy in some way. However, as I told you, we do this expansion and rotation. We can have the bilayer case. Actually, we can have more than the bilayer case. We can have, for example, vacancies. We can have absorption of molecules and so on. We can apply this method to different situations. And also we can consider different kind of materials. For example, here, I'm showing you the case of graphene, which is this light gray lattice here, and this is the unit cell of the graphene. Okay, now we have on the top or bottom or whatever the tungsten disulfide system. Also is a two-dimensional system, and this is the unit cell of this decalcogenide. Okay, and of course, to repeat this in the space, we need a supercell, and this is the supercell which is in green. Okay, so this is in the real space. So now we have two different kind of materials, and actually this second layer have two different atoms. It's composed of two different atoms. So what we have, for example, is again in red is the graphene brilliant zone, and in blue now it looks like purple because it's transparent, but this one corresponds to the tungsten the disulfide, no, the tungsten disulfide, okay, and this one in green is the irreducible or the brilliant zone of the supercell, and this is the irreducible brilliant zone. Here in each one we show the each one of the irreducible brilliant zones of the system. Okay. Now, for example, if we look at this system, now this is just graphene, just to show you how we operate this. We have an angle of more than 21 degrees, for example. So we have the red one, which is one of the layers of graphene, the blue one, which is one of the top, let's say the top layer of the graphene. We have these irreducible brilliant zones. We have this, which is the supercell brilliant zone, and this is the irreducible brilliant zone. So we obtain the electronic bands, which are these ones. Look at that, this is green, which is the supercell bands. Now we project these bands along the irreducible brilliant zone of graphene, for example, of this graphene in red. This is now what is the supercell bands projected on the graphene brilliant zone. And finally, what we do is to calculate the weights of this. And now what we can see is that some of the bands are totally reproduced. That means if the weight is 1, we are reproducing exactly the same states that graphene has. 0, that means that we are not reproducing that. And for example, we can see that these bands, which are that belongs to the states along the two-dimensional systems, remain exactly the same. All of them are red, for example, which is the weight 1. And but for example, we cannot we obtain that these bands here in red, for example, are not reproduced totally as the graphene because of the interaction of the second layer. Let me just to show you how this is. For example, here, we have the vertical stacking at 0 degrees of graphene. This is the graphene unit band structure. This is the tungsten disulfide band structure. Okay, all of them are separated far away, so they are not interacting between them. And now, for example, if we put in a distance and a shorter distance where they can interact, what we find is that the graphene band structure shows some gaps, okay, as well as here, the tungsten disulfide shows some gaps, and these gaps because of the interaction between the layers. Okay, so this is what we can do. Now let me just focus in the graphene vertical stacking. So now I can show you, for example, that, as I told you, at this angle of 21 degrees, I can show you that these states in red are unperturbed. These states, as I told you, are those that are in the plane. So they are not interacting between planes. That means because are in red. However, in these ones that are those which are the ones with the linear dispersion are associated to the vertical orbitals, for example, of the system. That means that they are interacting, these two vertical orbitals between the two layers, because I'm not reproducing as well. And in fact, if you remember at the beginning, this is only one band, and now it's split in two bands. And also we can find that here there are some gaps, okay? And these gaps becomes of the interaction of the second layer that does not allow the crossing of the bands, and they are unavoided crossing bands of the system. Now, if we look at the density of states of this, we can see that these gaps give us Van Hoff singularities here. Okay, these peaks becomes of these bands, so we can look at the density of states, and we can look at these Van Hoff singularities, these peaks. Also interesting is that, for example, these states are unperturbed, okay, which are those that belongs to the states alone of the two-dimensional materials. And for example, here, this splitting, of the band, that is because a kind of hybridization of the system of the orbitals belonging to the two different layers. For example, here we can see that it becomes the density of states, and then suddenly goes down, because here is the one band, and then it finished here because of the splitting of the band. Okay, so we can easily understand, for example, this density of states of the whole system in terms of this projection of the bands. Now, what happens when we have a smaller angle? Okay, now again, I'm showing here the reciprocal brilliance zones, and now we are showing here the band structure. You can see that now we have more peaks. Remember that in the previous slide we have 1, 2, 3 Van Hoff singularities because of these gaps. However, now we can see that we have 1, 2, 3, and an additional one that goes that is closer to the Fermi level, here to the 0, to the Fermi level. Okay, and when we reduce the angle, for example, now we have 9.9 degrees. Again, we have these peaks. We have here an additional peak, 1, 2, 3, now 4. But now we have this peak that belongs to these gaps that are going to the Fermi level as the angle of the system, or the angle of the interlayer graphene goes to 0. Okay, so to show you more easily, we have these gaps. Okay, to summarize a little bit, we have this gap that is going to the K point. Okay, we have these gaps that are between the K and M direction, high symmetry points. Okay, along these directions, and also we have this, which is the hybridization of the orbitals that belong to both layers. Okay, so this is for 21 degrees. This is for the 13 degrees. So we are going to smaller angles. Now we can see that this moved to be closer to the Fermi level. Now we can look that we have more gaps here, and these remain more or less the same. Okay, and now we have for a smaller angle, and again, as I told you, this goes down in energy. Okay, and now we have more gaps in this direction. So what we can find is that we reproduce some of experimental observations that, for example, these peaks on the density of states go to smaller energies here, okay? That this is the peak that we found around K, and that goes close to the Fermi level when the angle goes to 0. And also that means that sorry, because it's in Spanish, but that the charge or carrier velocity of the electrons diminish as the angle goes to 0 here. Okay, this is one of the physics that are behind of this interaction between the layers as a function of the angle. This is what the people found experimentally, which is more or less the same. This is the velocity, for example, of the bilayer charge carriers as compared with the monolayer, and we can see that it goes very fast at very small velocities as the angle, okay, diminish in this case. And also we can find that this Van Hoff singularities goes to 0, okay, for smaller angles as well. No? These are experiments. Now, what happened with the gaps and the that are around the endpoint, the aim symmetry point? As I told you, for example, we found more gaps, and for very, very small angles, we can see that these gaps became like discrete states. So now we have this is the angle between layers, and we are going down in this direction to smaller angles. And what we have found here is, for example, that we have these discrete layers, and that these states becomes separated by more or less equal energies. Okay, and this is some of the things that are interesting when you want to create different kind of optical devices, because now we, for example, we can have excitons, electronic transitions, and that and also you can control in some way the energies of these excitons and gaps as a function of the angle. Here, for example, to understand what is going on, we have this interaction between orbitals, okay, and we have the px orbitals that characterize the graphene, and these are, for example, the interaction in this direction, which is called the pp sigma, and also we can have the interaction. This is the orbitals along the planes, okay, and this is the pp pi interaction. And now to try to understand how the origin of these gaps and these discrete systems, we have these. We turn on and off, for example, these two interactions. Here is without interactions for a supercell, so we reproduce exactly the bands of the graphene as we expected. Now we turn on the interaction, the pp pi interaction, and not the pp sigma interaction. That means that we have interactions, let's say, along the plane, and this modifies very, very small the band structure. Now we have the turn on the pp sigma interaction and without the pp pi interaction. Okay, that means that this interaction is between layers. Okay, this is an electron interaction between the two layers, and now we can see that we can have these discrete and these gaps that appear in the band structure. And when we have both interactions, we still have this, and not much is perturbed because this in plane interaction, let's say. Okay, so as I told you, well, we have these states. These states now we are taking a small path along the supercell that is between the M and M K points of the two layers that compose the system. Okay, and we are now looking at these states. What we have is that found is that these states are projected in both layers. One, for example, is dominated here at this energy, for example, for the upper layer, and then for the bottom layer, the upper layer. So we look at that these discrete systems are turning, between the two layers. And also what we have is that we project here the wave function of them. And now in this side view, we can look that we have an state which is composed by the two layers. And what is interesting is that, for example, these states, as we project in the real space, we have regions where they are totally localized. That means that, for example, these electrons can travel along this direction, for example, and are not allowed to travel in this other direction. And also what we can see is that we can choose different energies, okay? And we can also have different channels where the electrons can move along the system. So this is the kind of things that we can look by doing this unfolding, and that it will be impossible to do if you don't have this kind of methodology to try to do it. This is, for example, what the people can see in a graphene layer with a molybdenum disulfide. You have these two layers, and for example, this kind of this kind of gaps and discrete states are observed by, for example, using angle. This is ARPS. Okay, I don't remember in this moment the name of the technique, but you can look at different energies and you can see that the discretization and the gap origin of the system. Okay, this is an experiment. So just to conclude, what that I have shown is that these twisted two-dimensional materials show interesting and new electronic and optical properties that we can control by controlling the angle between the two layers, the crystallographic orientation of the two layers. We can have different kind of interaction. For example, we can have these Dirac cones. We can have these mini gaps that can be controlled by the angle, by the interaction between the two layers. And also we can have this kind of hybridization and these discrete states of the system as a function of the angle. And as I told you, well, this unfolding method is very useful to understand the interaction and the different electronic properties, and also can give us some ideas of how we can construct another materials with the specific properties to, for example, to absorb molecule, to use like sensors, to use like another kind of electronic devices, and so on. Just let me thank to my collaborators, to Francisco Sanchez, who is the one who did the code, the post-processing of this. to Francisco Hidalgo, and Andres Botello, who also did the tie binding approach to try to understand the origin of this kind of interactions. And finally, well, we have some funds from CONACYT and also from the university, from the National University, from UNAM, which are called PAPITS programs. And well, let me thank you for your attention for the conference. Thank you very much.
Thank you very much, Dr. Cecilia. I wonder if there are questions. We have time. Go ahead, Paco, please.
Thank you, Dr. Cecilia, for your talk. I'm not an expert in this field, but I have a couple of doubts of how this graphene layers works, because as far as I know, you can use these graphene layers if you put one on the top of the other, like what you mentioned. But is it possible to control the height between the distance between one layer and the other in order to make capacitors, for example? But because in your case, it's not that you control that height, right? You just put one in the top of the other and study the rotation of one layer with respect to the other, right? And study the let's say the conductive energy, but along the layer, right?
Right. Yes. No. Well, because you have these van der Waals interactions, the distance. Once you have put one on top of the other, the distance is ruled by the interaction between them. So you cannot control. But what I want to show you is for a large separation, let's say, you don't have any interaction, so you can reproduce the electronic structure. And once you have separated the layers at a given distance, which is ruled by the van der Waals interactions, then you have this modification of the band structures. But not you cannot. I mean, the people can put in some frames these two-dimensional materials, and of course you can in some way modify the distance. Now the people also can control the angle, by for example they can deposit one graphene layer in some place and then to put another layer on the top, and with an AFM tip they can move, in some way, and they can rotate, but the distance is quite difficult to control. It's not possible, because of the interactions.
I see. Okay. Okay. So when you read about these graphene things, you found this kind of application, like as mini capacitors and things like that, or layers that could help as detectors, optical detectors for smell, etc. So in your case, what if you modify this angle in terms of the vertical stacking that you are doing? I mean, I understand from the basic, from the point of view of basic science, but is it possible to have some kind of application? What is the application of doing this rotation, the stack, the vertical stacking, or is just basic science?
Well, I mean, one is to control the mobility of the charges. Okay, so you can control the transport in this system by controlling the angle, for example. The other one that you can do is to control, for example, if you have these two layers, and then you have an incident electric field with a given polarization, you can control the angle between the two layers, and then you can change or you can rotate the polarization of the light. No, for example, in a typical way to control the light polarization and change, no, the light polarization, you need from the optical point of view, you need a system and a distance of at least the wavelength of the light, no, to change to rotate the polarization, or to change. In this way, because there are some phenomenology here that you can create some currents, and then you can change or you can create a magnetic dipole, and these currents are controlled by the angle. Then you can rotate in a few Armstrongs. You can change the rotation or the polarization of light. This is a kind of application, a direct kind of application that you can think in these kind of things. The other one is that in graphene, as I said, you don't have these gaps, so you cannot control the transitions or the transport, no, of electrons, and by changing just the angle between them, you can do it. This is the point. Or you can do, or also you can have these topological channels that then you can control the spin of the electrons in that way. No, the point is this is very, let's say, very new, and to understand what is going on is quite difficult. No, because these are very large systems in terms of the basics, which are the atoms and the electrons. And what we are trying to do is to look at what happened, no, in different regions of the energy, in order to control this transport or this optical stuff and so on. No? I don't know if I answered you.
Yes, perfectly. Thank you, Dr.
Okay.
Great. Thank you, Paco, for your question. Are there further questions from the audience? Okay. If not, we have to move with the schedule. But first, I would like to thank, on behalf of the organizing committee, to Professor Cecilia for accepting our invitation. It was a very interesting talk about the use of graphene, I mean, to understand the electronic properties. And as you explained us in the last part, some applications could be very interesting in soft condensed matter. Thank you very much, Professor Cecilia.
Thank you. Thanks to you.
Okay, so our next speaker is Dr. Miguel Ruiz Garcia from the University.
Okay,
Carlos
can you
III.
stop? Excuse me.
Oh yes.
Can you stop
sure.
sharing, because I lost the mouse in the. Okay. Thank you. I don't know.
Okay, there we go. Okay. Yes, so our next speaker is Dr. Miguel Ruiz Garcia from the University Carlos III at Madrid, Spain. And he's presenting a contributed talk, which is entitled Topology Controls the Emergent Dynamics in Nonlinear Flow Networks Towards a Excitable Fluidic System. So go ahead, please.
Thank you very much, Ivan. So I know that for you it's almost lunch time, and there were many talks before. I really enjoyed all of them. So mine is going to be a bit shorter, so I just ask you a last effort. I hope that you also enjoy this. So I know that the title of my talk is long, and there is a video here that you probably don't understand yet, but hopefully in the next 15 minutes, you will have a good grasp or understanding of what I'm saying here. And this is work in collaboration with Alejandro Martinez Calvo, who was at this university and now is a postdoc at Princeton, Eleni Katifori, who is a professor at the University of Pennsylvania, where I was as a postdoc until last year. So, okay, like this is the motivation that brought us to start thinking about this problem. I'm showing you some experiments here from Patrick Drew's lab. And basically you are looking at a window on the skull of a mouse, right? So it's a bit creepy, but you know, we can learn a lot of things from this. So the fact is that through this window, they can look at the vasculature. So you can actually see how much blood is inside the vessels. And this is the blood volume. So you see that these are the vessels, like arterioles around the brain. And you see that sometimes there is more or less blood, right? And it's fluctuating. And the other thing that they can also do is that they can put an electrode inside the brain and they can measure the neural activity, right? Like if the brain is active, is doing stuff or not, right? And what they find is that the fluctuations on the blood are correlated with this neural activity. And it makes sense because, you know, if your brain is doing something, it probably needs more nutrients. So you need more blood, you send more blood to that region, and that's probably why it's correlated. But the striking thing is that there is some part of the oscillations that are not correlated. And you could think, okay, they are maybe related to other neural activity that your sensor is not getting, probably from the nearby regions, right? But the fact is that they can infuse some medicine to the brain so that there is no neural activity now, right? Like the brain is like completely shut down, and still they see fluctuations, right? And they are smaller, so they are like this part of the fluctuation that were not correlated with neural activity, and now we actually can see that it's actually not coming from neural activity. So this made us start thinking about like what could be the origin of fluctuations in vessels, like in flow vessels, if they are not externally controlled, right? Like, can they be intrinsically produced by the flow action? So, you know, we had to learn a little bit about the physics of blood flow. We think that there is two main ingredients that are really important to be able to explain why, or one reason how these fluctuations could appear, right? The first ingredient is that if you look at, you know, vessels and arterioles are complicated, really. These are, you can imagine that they are pipes, but they have muscles, they are alive, they have different responses depending on different like inputs. But one thing that you can see is that when you control the pressure difference between the input and the output of a vessel, an arteriole in this case, and you increase the pressure difference, the flow starts increasing. But then there is, and you would expect that, right? Like the more pressure difference through a pipe, the flow increases. So a linear response would be like Poiseuille flow, right? So this increases, but at some point it actually decreases and then increases again. So there is a region of a negative slope, right? And this is already hinting us, this is telling us that this can actually produce a lot of complex dynamics. The other ingredient that we think is important, and I think this is pretty intuitive, is that as we saw before, sometimes there will be more or less blood inside a vessel, right? So when you have a volume accumulation like this, there is some external medium, like the medium that is outside your vessel, your arterioles, that is actually, in this case, contracting, right? Like is deforming, and because it deforms, it actually imposes some pressure nearby. So there is a coupling between volume accumulation and pressure. If I want to be a little bit more quantitative, I can do some simple simulation where I took a block of an elastic material. We impose a volume accumulation in the sense that we impose external pressure here so that we deform the medium, and then we measure the pressure response of the medium on this boundary that is actually clamped. And what we see is that on the free surface, the response is actually exactly the same that I'm imposing because a free boundary, right? But outside this region, there is a pressure response that decays, and it depends in this case of the Poisson ratio. So it depends on the elastic properties of the medium. So, you know, we have these two ingredients, only these two ingredients, that is like a nonlinear relation between flow and pressure difference, and a coupling between volume accumulation and pressure. How can we put everything together in a model where what we do is actually we simplify things a little bit more. We take a network of edges nodes, and we will compute the pressure at every node. So an edge is gonna carry some flow depending on the pressure difference between input and output. And because we want to account for volume accumulation, we want to study this problem where we can have more or less volume at any point of the network at any time. We will actually account for the volume at the nodes, right? So this is another simplification that we do. So now the expression that we use for the current through a vessel depends on the pressure difference. It depends with this gamma function that it can be either linear, like Poisson flow, or it can be this nonlinear relation that we just discussed with the negative slope. And we also multiply by the volume, because of course, if we are sending current from one node to another, there has to be some volume here so that volume can go, right? If volume is zero, then the current is zero. And the other ingredient is what we were discussing before, that there is a coupling between volume and pressure. And we introduced it in the simplest way that we thought, that is like, it's something like the Poisson equation, right? Like we have, this is the graph Laplacian. So you can imagine that in the continuous limit, this is the Laplacian. It is applied on the pressure, and this is like a source, right? So if you have a volume accumulation, actually the pressure will increase at this point, and it will decay far away. So now we have all our ingredients for our model, and we can try to solve the equations. Actually, in 1D, if we have a network that is 1D network of these edges in series, we can do analytics, and we can study what are the stationary solutions, which of them are unstable, stable, or which one can be oscillatory. So what we find is that if we impose a pressure difference, like this is your network, right? Like the position in your network, and this is the pressure at the entrance, and the output is zero. So if you impose a pressure so that it lies on the negative slope, we can prove that this is unstable and unstable solution. And the stable solution would be like two domains, like two regions like this, right? And we actually can show that if the network is long enough, you can have like solutions like this. You see, there are like three domains like this, and they can actually travel and recycle, and then you have oscillation. So we can see, if we can see this in simulations. Actually, we can even do it in a complex network like this. It's a planar network with periodic boundary conditions, and I want to stress this. We are imposing a constant pressure difference between this node and this node. It's like a constant DC battery. I'm going to plot here pressure with the color around every node, and this is going to be volume with the color around every node. And what you see is that even though I'm imposing a constant pressure difference, there are oscillations, right? Like there are oscillations where the volume accumulates around the source, and then at some point it detaches. There is a pulse that travels, it reaches the sink and recycles again and again. So, I mean, of course, this is not a proof that is what is going on in the mouse brain, because this is a very simplified model, but I think it's a proof of principle that in this very, very simple toy model, you can get oscillations with a constant pressure difference just because of the nonlinearity in the flow, and because of the coupling between the volume accumulation and the pressure difference. So we actually played a lot with this model, and there are many things that I can show you. I can show you, for example, that it shows excitability, in the sense that in this case, this is a very long rectangular network, right? I have like 100 edges in this direction and only 5 in this direction. And if I impose a pressure difference between the input and output, that is this much, this is an equilibrium point, right? Like nothing happens, there is flow going from left to right, but there is a homogeneous distribution of pressure and an homogeneous distribution of volume. But what happens is that if I now introduce a pulse, oh, sorry. If I now introduce a pulse in the pressure, I actually triggers a pulse. I trigger a pulse in the volume, a wave that is traveling from left to right. When the wave reaches the end, it goes back to the equilibrium point. And if I introduce a new pulse, there is a new wave. And the funny thing is that if I try to introduce a second wave while the other one is traveling, actually nothing happens. So there is like a refractory time. So these are actually all the phenomena that an excitable medium has to show. As you see, it is not excitable because the ingredients or the elements are excitable. Is it excitable as a global phenomenon? So, you know, we were very excited about this. What else? I can show you all other behavior. Like, for example, if I introduce linear edges in the middle, like this circular region of linear edges, then the waves they jump the region, they leapfrog the region. Thinking about this kind of problem, we realized that we could do several modifications to our network. For example, we could take the input and the output and put it closer together. We could introduce more linear edges, or we could introduce shortcuts. And what we saw is that for these three different changes to our network, the frequency was increasing. We were thinking about this, like, because they are very different changes, and still the effect is the same, that the frequency increases. And what we thought is like, okay, how could we measure in the same metric what is happening to the network with these very different changes? What we thought is like, okay, if I put my source and my sink closer together, it's obvious that the path between the 2 points is shorter. But if I introduce shortcuts, somehow it feels also short. The path between this point and this point feels also shorter because, as its name says, I'm introducing shortcuts, right? So what we thought is like to compute this with a random walk, and because this is a flow network, I have here like a random fish. So as this fish is randomly jumping from one point to another, the escape probability, the probability that it reaches this point without coming back to this point, actually increases as you increase more and you put more shortcuts, or as you move these points together. Now we can use the same metric for all these changes, and actually, as when you plot the frequency of the oscillations against the effective distance measured with this escape probability of the random walk, all the frequencies for, you know, introducing more shortcuts, more linear edges, or putting the sources together, they collapse in the same line. So, you know, we think that this topological metric, the escape probability of the random walk, is a meaningful metric in this problem. And to finish, like, you know, I wanted to tell you something else, that probably we realized that we were maybe too far into theory land, and we wanted to maybe to go back to reality, right? And then we started to think if we could actually build this in the lab. So if you want to build this in the lab, you need something like something simple valve that can give you like this relation between flow and pressure difference. And actually we realized that this was not too hard to produce, right? If you have something like this, as you increase the pressure difference, they will close and then open again. And, you know, depending on the length of these beams, they actually, you can find pretty easily this relation. So we have our first ingredient, right? And then we needed a second ingredient, that it was the coupling between volume accumulation and pressure. And we also think that we can get that, right? Because if we have an external medium that is an elastic medium, as we discussed before, you can have like a volume accumulation here, and it's going to produce like a pressure increment nearby. So we think we have all the ingredients, so we can put them together. And this is very preliminary work, so we are still working on this. So, you know, be tuned. I hope to show you more things in the future. But we can start to see like the phenomenology that we discussed at the beginning, right? This would be like our 1D system, and you see how there is a pulse that travels, and actually in this case, it finds a stationary solution that actually agrees with our theory, right? The thing that we discussed before, where this solution should be unstable, and then the stable solution is like a formation of two domains of low pressure drop and high pressure drop, and actually that's what we see. And then we even thought like, okay, could we see the unstable solution somewhere? Well, actually, to get this solution, you need to have a volume accumulation here. You see that this region is like expanded. So if we impose external medium that is completely rigid, we will not be able to have a volume accumulation here, and hopefully we will be able to recover this solution. And actually we do, right? Like if we impose an external medium, we find the unstable solution. So with this, I finish. I hope I was in time. I think so. So I will leave here my conclusions, but before finishing, I want to thank the funding. Now that I am at Carlos III University, I have funding from the university and from the Marie Curie fellowships from Europe. This is the funding from where I was as a postdoc in the US, where this work was also done. You know, I thank my collaborators, Alejandro and Eleni, and thank you very much for listening.
Thank you very much for your interesting talk. We have time for questions. I wonder if you have observed this phenomenon in vivo tissues, or can you observe it only in dead tissues?
Okay, so you mean like the experiments that I showed you at the beginning?
Yes, exactly.
Okay. In that case, the mouse is alive.
Oh, okay.
Yeah, I mean, it's a bit, you know, it's not the nicest thing to do to an animal, but it's alive. And basically you avoid, I mean, it's constrained, right? It cannot escape, but it can move. I mean, basically what they actually do is like they puff some air on the whiskers. So the mouse moves the whiskers, and they know that this is the region that controls the whiskers. That's why they can control like the activity of this region. And in the second part, the mouse is still alive, but now it's like in coma, right? Like they basically shut down the brain, and still in coma, right? Like they can see these fluctuations. I mean, this is important because there is a lot of debate about rest state fluctuations in the blood, even for humans, right? But in humans, they cannot do that, right? They cannot open a window, right? But still they see that there is like a rest state where the blood in your brain is oscillating, and there is a lot of controversy about like if it is related to some standby neural activity, right? Like your brain is doing something even when you're resting or even when you are in coma, right? Or this work, right, from this lab, Patrick Drew is at the Penn State. What they suggest is like, you know, maybe there is some part of the oscillation that it doesn't have to do anything with the brain activity, right? But there is a lot of controversy about this, so I don't want to take sides.
I see. Thank you very much for clarifying. I mean, the experiment.
No, they are. I mean, they are very cool experiments, I think.
Yes, indeed. Okay, we have a question from Paco. Please go ahead, Paco.
Yeah, thank you. Thank you, Ana, and thank you, Miguel, for your interesting talk. And maybe I need to go to the details to the paper, but for me it was quite difficult to not compare your methodology with a typical Lattice-Boltzmann simulation for fluid. In terms of the channel that you show, and what you put there are nodes that, and you follow in certain way the pressure and the velocity on each node, right?
Yes.
So in that sense, it's similar to Lattice-Boltzmann, but in Lattice-Boltzmann, what you follow is the velocity of each node that represents, distribution of the velocities of the flow. But in your case, you just follow certain rules on the pressure, right? Well, you follow the Laplacian of the velocity.
Yeah, I mean, I guess,
but
so I would need to think harder about this, right? So I'm going to answer whatever it comes to my mind now, right? But we can maybe talk more about this. I guess maybe the easiest way to think about this, like you could think about this like a network of resistors, right? Like current resistors, right? Like a DC battery connected to a network of resistors. And the only thing is that these resistors are non-linear. So they do like this.
Mm-hmm.
And because they do like this, if they were linear, imagine, right? If you had a network of resistors, if they are linear, you change something in the boundary conditions, everything is satisfied instantaneously everywhere, right? Because, linear resistor, they only have one solution, right? So if you change something, everything has to change at the same time. But if the resistors are non-linear, then you have many solutions, right? And actually you can have waves traveling in the system. But to get that, you also need to be able to store volume. It's like this would be, it's not the same, but it would be related to having like capacitors in your system so that you can have more or less volume in every place. So if I had to draw an analogy between what we do and something, that we are more familiar with, I would think in a network of resistors, but the resistors are nonlinear. I would think on this equation as something like having capacitors so that you can have more or less volume, and it's coupled to the pressure. That would be like voltage in the case of the resistors, right? And about the analogy that you mentioned, I would have to think about, like, it's possible that is there. I don't know.
Yeah, because it's difficult for me to think how you choose the distribution of your nodes, right?
Oh, so you mean like
is just totally random?
Yeah, I mean, like, yes. I mean, like in this case, I only wanted to have like a planar network of channels, right? Like, and I mean, I can tell you how I did it, but it's basically a planar network of random edges. Because I just wanted to have, so okay, like, I mean, this is theoretical, it's a toy model, it's far away from the brain, right? But if you think about the brain, what actually happens is you have like a surface of arterioles, like arterioles that are feeding your brain. So you have like it's actually almost 2D, it's covering your brain, and then you have penetrating arterioles that are going in. To this surface, you basically feed it with one big vessel, right? So this would be like the toy version of having a surface of arterioles, and then you could include like many things that are like the penetrating arteries. But I am aware that this is like very, very simplified.
Okay, thank you, Miguel. Really interesting.
Thank you very much.
Okay, we have one question from the audience, from Claudia Elena Ferreiro, Córdoba. Go ahead.
Hi, yes. Hi, Miguel. You just mentioned something to Paco. You said that you just wanted sharp edges, but I mean, I look at this picture and mainly see triangles. I see other kind of geometries, but I mean, and you also said that you play with like adding shortcuts, but does the geometry of your like network also has an impact on your result?
Yeah, I mean, yeah, that's a great question. So, okay, in our case, the way we created this basically, okay, it doesn't matter too much, but you can see by eye that it's like some disordered pattern of triangles, and sometimes you have some square or whatever. I'm not considering that the length of the edge matters. I could, right? I could include here something that depends, that the current also depends on the length, and it could be even more realistic, but we didn't do it because we wanted to have the minimum amount of ingredients so that, we could explain the behavior. What it really matters, as you realized, I think, is that like the topology of the network, right? Like if I have a shortcut that goes from here to here, now a pulse can like really like teleport from one point to another, right? Because there is a shortcut. So that really matters. In that sense, also this is, you know, when we have the 1D network, it behaves differently from this one that is like 2D or planar. And if you have like a complex network with a lot of shortcuts, then it may behave differently. And the nice thing is that even though they are different in many ways, we introduced this topological metric that I explained it very fast. So I don't know if you got it, but it's basically, regardless of the network, with this random walk, you can measure the size of your network in some way. And it helps you to predict the frequency of the oscillations.
Okay, thank you.
No, thank you very much for the question. Oh, Ivan, I think you are muted.
Oh, yes, yes. Thank you, Miguel. So we have time for more questions.
I know that my talk was the last one before lunch, I guess, so I understand.
Yeah, yeah. Maybe people was a little bit hungry.
But yeah, I was very happy with the question.
Okay, well, I think it's time for lunch. So I would like to thank you, Miguel, for your presentation. Very interesting. And I would like to remind everybody that we will continue at 4 p.m. Mexico City time with more contributed talks, starting with Pedro Ramirez Gonzalez at 4 p.m. And we will have a very interesting contributed talks this afternoon. So thank you very much to everybody. I do not know if Paco or Julio have some announcements.
Yeah, so thank you very much for giving me the opportunity to share my work. I really think that the conference is working very well for, you know, being everything virtual. I think you are doing a great job. Thank you.
Thank you very much, Miguel.
Hi, Ivan. No,
Hi, Julio.
I don't have any announcement. No. Yes, I just back.
Paco is. Paco, do you have any comments?
Sorry, I just keep the hand raised, so, but there is no announcement at all. I mean, just to remind you that the posters are there to see the posters, and if you have questions to the participants, please go ahead in Twitter, or you can send emails or whatever, or use the Gather Town application also. Thank you.
Great, thank you very much, Paco. All right, so it's lunchtime. So thank you very much for attending this section, and I will be very happy to see everybody in the afternoon.
Okay.
See you then.
Have a great lunch. See you later.
Sure, see you later.
Bye.
Bye. Julio.
Hey.
Who is the next host for the afternoon?
I guess it's Gabriel. Just let me check.
Okay, but Gabriel isn't here.
Yeah, let me just to
okay.
verify.
Okay, it's okay. I mean, it's not you, so okay.
Yeah, but I have the information here, so just give me a second. Okay.
So should I continue connected, isn't it?
No, it's Victor.
Victor, okay.
Victor, yeah.
Okay, yeah. I'm host, so I will arrive a little bit before to make him host.
Yeah, okay.
Okay.
Yeah.
See you later then.
Bye.
Thank you, Julio. Bye.